Yeah. So let's come back to using the matrix as a function, right? So let us consider a matrix A, uh, which is uh, which is a 3 cross 2 matrix. So uh,
You want a rectangular matrix, right? So it works as well. It's 2
yeah.
plus 3. That's it.
No, I thought first
Okay.
we'll go
Okay. Yeah, go
from
ahead. Go
three
ahead.
cross two.
Go ahead. So 1, comma 2, 3, comma 4, and 5, comma 6.
Yeah. So we have this matrix A, which is a 3 cross 2 matrix, right? So let us see what this matrix is doing to uh, what this matrix is doing to
A vector.
the R3 plane or any right, any vector in the R3 plane, R3
Hmm.
set. So I'll take a vector V. Uh, why is this not giving an answer?
Isn't vectors should be like
Okay, right.
2 cross?
Yeah, sir. So we have this vector 1 cross 2, which is in the R2 plane, right? It is in the XY coordinate. And when we apply this function A on this function pulls it into the R3 plane. And yeah, so when I take a vector in R2 plane, in XY plane, and I pre-multiply it by this matrix A. When I apply this matrix A to that vector, I get a vector in 3 dimensions. How do we like see this in how do we how do we know that we are getting this in 3 dimensions, right? Because we have given it only 2 inputs. So we can we can use that interpretation where we can write A as a linear combination. Sorry, we can write the AV multiplication as the linear combination of the columns
Of matrix.
of the A vector of matrix A, right? So in this case, uh, that would be 135 times 1 plus 246 times 2.
Correct.
Now we gave that 2 inputs, 1 and 2, and we got an output of uh, 3 dimensions. Let us consider the other case,
Okay.
the
So
two, three.
just a second, Atharva. So we took a matrix 1, 2, 3, 4, 5, 6, right? That's a 3 cross 2 matrix. And we took a vector that's in R2, correct? 1,
Hmm.
comma 2.
Yeah.
and we multiplied that vector, or we, in other way, we can say we gave that vector as an input to the matrix A, and it gave us an
Yeah.
output 5, 11, 7 in R3. We gave it an input in R2 and it gave us an output in R3.
Yeah.
Okay. And you said, okay, we can think of it as like linear combination of column vectors of matrix A. That is 1, 3, 5 multiplied with 1 plus 2, 4, 6 multiplied with 2. And it gives us 5,
Yeah.
11, 17. Right? Okay.
Yeah.
Yeah, good.
So basically, we are taking a two-dimensional vector into three dimensions.
All right.
Uh, let's take the other example where I have a matrix B. Now, this is a 2 cross 3 matrix, right? So I can give this a three-dimensional input. So I'll take a vector, a random vector in three dimensions, right? So I chose 1, 1, 2 just because I like that vector.
Mhm.
And I applied the function B on the vector U. What I see is I get a vector, output vector in the XY plane. I can change this vector and still I'll get output in XY plane. In fact, here you can see that it is not even showing
Maybe not in XY
the
plane, maybe R2.
zero.
R2 would be
Like,
the correct way to put it.
yeah, R2. It is not even showing z is equal to 0, right?
Right.
So basically, it is impossible for us to get the third dimension here.
Correct.
So let us discuss what is happening here. When we take any matrix, any function, we can consider it as we can look at it in this way also, right? The first column of the matrix, it takes the original basis, one of the original basis vector to 1, 4. The second one takes one of the basis vector to
2,
2, 5. Third one takes third vector to 3, 6, right?
right.
So yeah,
That's our matrix B.
basic that's our matrix B.
It encodes
So
this information where it takes the basis vectors of R3 that are uh, the unit vectors of the matrix B. It encodes the information of taking where it transform them, how it transforms them, right?
Yeah, so
yeah,
I cap goes to the first independent vector in the in the matrix in the column in independent column in the matrix, and the
Right.
J cap to the second, like that, right? Yeah.
Correct.
Okay. Okay.
Yeah, go ahead.
I,
Go
I
ahead.
have a question.
Yeah, Vinay.
So I cap in R3 is 100, right? But I can never even input 100 to this, right? So what do you mean by the first column represents where 100 is going? I mean, I can't think of it as basis vectors now.
Ah,
Right?
yeah,
I
yeah, yeah.
can't.
Atharva, can you input 100 and multiply that with B?
yeah.
Just create the vector 100 and multiply that with vector B. Interesting. It gives me 1, 4. That's also the first column of the matrix B. What happens when we give
Yeah,
an input of 0, 1, 0?
that's
Right. Oh, it gives me the second column now. Okay. Okay. Very interesting. And what if we give it 0, 0, 1?
now we got the
Okay.
third column.
Okay. Okay. Oh, interesting. So we gave it some inputs that are the unit vectors in R3, and it gave us the columns of this matrix B. Okay. So we can see that. Okay, that's what you meant when you said, okay, it encodes that information where it maps those unit vectors. Interesting. Okay, yeah,
Yeah.
go ahead.
Now because this first vector 1, 4 lies in R2, 2, 5 also lies in R2, 3, 6 also lies in R2. That means our final vector, the output vector, that should also lie in R2. That's why we are getting only 2 dimensions in our output vector. So now consider we have just a minute. Yeah, let's take another example. Now I have this matrix, row matrix 1, 2, 3. I want to multiply a random vector to this matrix, and I will observe what happens when we multiply it.
Okay, perfect.
So
So we
let's
have
see.
now 1
We
cross 3
multiply.
matrix.
Yeah. Why is this not giving answer again? 1 cross 3, 3 cross 1.
You're multiplying 0, 0, 1 with this, right?
Yeah.
Okay. So you multiplied. Okay,
So
maybe
1
do
cross
one
3.
thing. Maybe do one thing. Instead of C equals to this bracket, okay, this is matrix, right? You created a matrix.
Yeah.
Okay. Is it a matrix? Can you do flower brackets again? 1, 2, 3. Okay, yeah. Just directly do C times U.
See asterisk.
Shouldn't give us this. Okay, maybe do one thing. Can we multiply 2 matrices in GeoGebra, Vinay? Maybe try inputting this 1, 1, 2 as a matrix and try to see if it works as a matrix if we multiply it as a matrix.
Yeah, but it won't output the matrix, right? I mean,
I
matrix can be shown on YouTube.
yeah, I doubt it will do it, but let's just try. Or maybe we can do one thing, Sarva, you can figure that part out. Till then, I think Sir can take over.
Yeah, sure.
Yeah. Okay. You try to figure it out and we'll continue from there.
Yeah.
So are you ready?
Yeah, I was waiting for you guys to finish. If you're done, I'll join in 2 minutes.
Yes, sir. We're done, sir.
It's going to be for 2 minutes. I'll join at 9:25. Huh?
Sure, sir. Yeah, Tharva, did you figure that part out? Okay, let me see on my end as well. How can we do it? So you took
Yeah, yeah.
hmm,
So I got a matrix which is just one dimensional, which makes sense because you're multiplying a 1 cross 3 to 3 cross 1, right?
right.
So we'll get a 1 cross 1 matrix. What does this product signify? What does matrix C times matrix D signify?
Hmm.
Anyone?
Sum of the corresponding entries.
Oh, Vinay, your voice vectors.
Yeah, that's fine. Is the fan ratio? I'm not sure. Can you
Yeah,
hear me now?
yeah.
Okay. Sum of the corresponding entries. I mean, 1 is being multiplied with 1, 2 is being multiplied with 1, 3 is being multiplied with 2, and the sum of it.
So dot product you
Yeah,
said.
yeah.
Hmm.
Yeah. So uh, surprisingly, this comes out to be the dot product. Now, why this comes out to be a dot product, we'll see that sometime later. But this basically signifies that I have taken a projection of 1, 1, 2 vector onto 1, 2, 3 vector, and I am reporting the magnitude of the projection.
Interesting.
How long of a projection does vector D make on vector C?
Right.
So, drawing similar analogies, we can consider matrix A. Uh, uh, we can we can consider matrix B that projects the vector 1, 1, 1, 0, 0 onto the plane xy.
Interesting. So it takes a three-dimensional input and projects
Yeah,
on the plane XY.
yeah.
Okay.
So we took a 3D input, we projected it
Hmm.
on 2D planes. How are we projecting that? We'll basically find the projection of u vector on the first row vector, and we'll find the projection of u on the second row vector, and we'll scale the uh, basis vectors of R2 in that linear combination.
Oh, okay. Understood.
Uh, I really think I'm not clear. So I'd like someone else to explain what I explained back to me to just
Yeah, just
make
maybe
sure.
explain me as well what Atharva said. Anyone? Maybe Vinayak? Vinayak, are you there? Vignesh?
Thank you.
Or anyone? Swapnil, maybe Shriram, Praneeth, Kartike, Chitturaja, Bharat Anurag, anyone? Just maybe put it on in your words what Atharva was trying to explain there. Nishan.
I just joined, Chetan. Hi.
Hi. Yeah, Anurag, did you understood that?
I kind of understood the first part, like when he said he took the dot, I mean, when he tried to apply the vector D on the matrix C, and C was just one row vector, one row matrix, right? I realized that in that sense, it's just a dot product. And the dot product
Yeah.
kind of signifies the magnitude, right? Because you take the magnitude of the two vectors, you multiply them, and you have the cos theta in between. And the angle also kind of matters.
Yeah.
So if I try to project that to the next the B matrix, how do I go around that?
Yeah, maybe
Yeah.
rephrase
So
that whole projection thing, Atharva.
yeah. So basically we can also see that using maths, right? So when we multiply b vector with u vector, what we are doing is we are taking the first row vector 1, 2, 3, and we are taking its dot product with u vector.
0, 0, 1.
Yeah, 0, 0, 1. And to find the second value of the output, we are taking the second row vector and taking its dot product with the
U vector 0, 0.
u vector 0, 0, 1. So, and when we put that together in a matrix, what we are getting is basically the projection of u vector on 1, 2, 3 vector times I cap, and projection of u vector on 4, 5, 6 vector times j cap. So basically we are scaling I cap and j cap with respect to the projection of u vector on each row vector of B.
Here you mean I cap of R2, right? Because
I cap of R2, yeah. 1, 0 and 0, 1.
maybe that's why it's not very clear for me, because I think there are 3 elements that I'm multiplying. But okay, when I think
Yeah.
of 1, 2, 3 itself, I realize, see, 1, 2, 3. See, when you said that the first column, second column, and third column represents where 1, 0, 0, 0, 1, 0 goes and 0, 0, 1 goes. I understood that because when you tried to input them, I saw that it was just equal to the columns. But when I tried to see the dot product from the row wise, that happens to be multiplied with the I cap, it's like, okay, it's like crossing over somewhere, but maybe I'm not able to understand that.
Okay, so we'll take some example. So I'll change up this value. Yeah, so now I change the u vector. I have this u vector. Now, when I'm multiplying B matrix with u vector, what I'll do, I'll take, to find the first element 3 here, what I'll do is I'll take 1 times 2, 2 times minus 1, 3 times 1, and I'll add them. And I'll input them in the first box here. To find the second, what I'll do is I'll multiply 4 with 2, 5 with minus 1, 6 with 1, and I'll add them and put them here. So what I'm doing is I'm taking a dot product of the row vector of B and this u vector and putting it in each column, each box here.
So the putting in the box is what you're trying to say is multiplying
Yeah.
with I cap.
So what I can, I have 3, 9, right? So what I can do is I can express this vector as 3 times 1, 1, 0 and 9 times 0, 1. If I'm...
So you can express that itself as a linear combination of I cap and J cap.
I cap and J cap in 2 dimensions, R2.
3 times 1, 0 plus 9 times 0, 1. Yeah, okay. Yeah. Yes, sir. Sir, I think.
Yeah. Okay. Okay. Thank you, Tharwa. So you can take over now.
Yeah, one moment. I'm connecting on desktop. Huh?
Sure, sir.
So meanwhile, what were you guys discussing?
So we were planning to discuss least squares, but Atharva felt that there are some concepts we must discuss before that. So we were just discussing that basics of matrix.
That 3 is coming from the dot product, right? So when we got the output as 3 and 9. So when you want to represent it as a linear combination of I cap and J cap, you just have to understand the dot products. Okay, that's what you're trying to say. The coefficients of the linear combination of the I cap, J cap, or K cap, and how many ever basis vectors we have.
We'll try to do one thing. We'll write it down. We'll write it down and see.
Yeah.
It will be
Yeah. Yeah. Very nice. That's a very nice view of
Yeah. So basically, we scale those basis vectors by the proportion of their projections
projection.
on the two row vectors.
right.
That we can kind of relate it to like a dot product in 2 dimensions, maybe.
Hmm.
Sort of.
Okay, we'll discuss it. We'll write it down and we'll discuss it.
Yeah.
But most probably tomorrow, not today. Atharva has to leave early. He might not be able to stay in the session for long. So we'll be discussing that part tomorrow.
Kind of
Vectors,
related
Maria,
to,
vectors.
sorry. Yeah, I mean, something that I kind of related what you said to is, normally when we, okay, no, that's not the same thing. Yeah, my bad, yeah.
We realize what you did there, right? You posed the question, answered it yourself.
Yeah, I like what I thought was that it was like when we usually take when we find the projection of a vector, like now we are actually taking like our dot production our dot product is the projection on I cap, right? The dot product of the row vector with the
Vector U.
yeah, with the vector u is a projection on I cap. So something that I thought was usually if we take projection of u on v, it's u dot v times unit vector along the direction of v, right? So something I thought was, but we're not actually taking the projection like dot product with the I cap vector, right? So that's why I got confused. And, yeah, it's not the same. Yeah.
Do you guys have your writing aid with you? I think so. Can let us know when he's ready. I think till then we can write it down, and otherwise here we can maybe discuss by writing it down so that everybody else understands this as well.
You can try.
Atharva, are you here?
Yeah.
This gives us 3. So this gives us 3, right?
Yeah, it gives us 3.
Okay, people, I'm sorry, there was some problem with my internet connection. Otherwise, the internet going good?
Yes, sir.
It was
Using
low.
Wi-Fi or direct?
Yeah, bandwidth was low
So
for a
both
while.
are working.
Pardon, Atharva?
No, I am on my hotspot, but LAN is also working.
LAN is also. Why are you on hotspot?
It is just convenient for me to use my hotspot. That's it.
Yeah. I mean, even I have been using my hotspot only because some problem with the internet connection. So if my internet goes away, I will switch on to no video mode. Okay. All right. So let me share my screen. This is just for my reference so that I know which day what was covered. Okay, so I've been observing that you people are growing with your thoughts, which is a very good thing. It's time for us to discuss something more mature, which we have been doing with time, but then now we have come to a stage where I think any aspect of linear algebra we can basically discuss. All right. Before going any further, I'll discuss a couple of results that are actually pretty straightforward, involves derivation, but intuition-wise, at least, I don't think certain things have intuitions. At least I have not found intuition for the following concepts that I'm going to tell you people. Not something that I can explain very quickly. There is intuition behind it, but then it will be a roundabout intuition. One moment. So our first question would be, a couple of results. We'll revisit these results later, but I'm just introducing right now so that you can be familiar with it. This we know is a function. N cross n matrix is a function like this. And n cross m matrix will be from Rm to Rn, right? We all know that. Of particular interest are matrices that are symmetric. Okay. Symmetric means across diagonal, it's the same. What does it even mean? We get these kind of data sets very often. Okay. Distance from I to j, if you represent that through matrices, distance from I to j will be equal to distance from j to I. Correct? Makes sense? That's a symmetric matrix. But then not all matrices are symmetric. In fact, many matrices are not even square. You get rectangular matrices, but they have one small property that when you multiply them with their transpose, this becomes symmetric. Now the question is, why would you even multiply a matrix by transpose? We'll come there later. But just note that symmetric matrices occur in nature. Distances, pretty obvious. From I to j, I location to j location, if it is 2 kilometers, from j location to I location, it will be 2 kilometers. And if you are writing down the matrix of all possible areas to area distances, ijth entry will be same as the jith entry. Okay, pretty obvious. Now, this symmetric matrix that you get here, we also get when we take any matrix and multiply it with its transpose. Why would we do that? We'll answer that in our journey to dimension reduction that we've been discussing for a long time. In fact, we'll be continuing to discuss that for a long time because good amount of data analytics starts and ends there. All right. Okay. So the symmetric matrices are very interesting for the following reason, that any symmetric matrix S has eigenvectors perpendicular to each other. This takes a few weeks to grasp. I'm going to discuss what we'll be discussing for the next couple of weeks, encapsulated in this one page. Okay, whenever you have time, just write a symmetric matrix and stare at it. Just recollect the definition of symmetric matrix and then try to sort of internalize it. Understand what are eigenvectors and know that symmetric matrix ka eigenvectors jitna bhi hai, all those eigenvectors are mutually orthogonal. Okay. If you want, you can open NumPy and then try this. Can someone open NumPy? And Atharva, are you around? Atharva, Chetan, Srivinay, one of you?
Yes.
Just
sir.
open NumPy. Share the screen.
Are you sharing or should I go ahead?
Go ahead, Vinay.
Okay, so what we will do is we'll open NumPy and create a symmetric matrix. Okay.
So how big?
Yeah, take any matrix A, consider A transpose, you will get a symmetric matrix. That's all. Four, five, six. Yeah. 4, 5, 6, 7, 8, 10. 7, 8, 10. Okay. And consider A transpose. I think A dot capital T gives you the transpose, right?
Yes, sir.
Into A.
At the rating.
We got the symmetric matrix, right? So show me the eigenvectors of this matrix. NP dot Linalj Eig. Okay. Multiply the first two columns and see whether you get 0. If Atharva is around, maybe we could have used this thing, what Copilot. That will be quicker. And
Atharva, are you here?
Yeah.
Atharva, if you're busy with some quiz or something, we will not disturb you. Don't worry.
No, sir, I'm here for like about an hour or so.
Okay, good then. Why don't you just do the same thing using, because we may require a little more stuff, Rivana. It will be difficult for you to do it. This is the first.
Okay, sir.
Is it the first row or first eigenvector is in the first column, right? No? Okay, let's see. Do the dot product of U and V. You may fall. Careful.
Yeah, small error, I guess. You can go ahead, Chattanooga.
Yeah.
Otherwise, just open Vim with Git Copilot and
Yes, sir. Yeah.
yeah, perfect. Find out the product of two eigenvectors. That's all. Yeah.
Yeah, we got 2.7755 something.
No, that is 0, no?
Oh, okay.
1 over 10 to the power of minus 16. You know?
Yeah, almost 0.
And make it for 1 and 2. 0 and 1 you saw. Make it for 1 and 2. 1 and 2 and 2 and 0.
I didn't get them.
No, these were two eigenvectors, 0 and 1.
Yeah.
Do it. Go to the code.
Yeah.
Instead of in the last line, instead of 0, make it 2. That will be the product of two eigenvectors, right?
1 and
Second column and first column. Yeah. Look at this. No, anyway, you already had 1 there. No, that's why I thought you can make it 2. All right. Anyways, no mind. Shift J will make it go up. Yeah.
Yeah, 10 raised
Even
to
this is
minus
0.
14.
Right? 10 to the power of minus 14. 4.5 and 10 to the power of minus 15. Okay. Make it 2 and 0. Basically, 3 eigenvectors, right? All 3 choose 2 possibilities we are seeing. I'm sorry, 2 and 0. Yeah, make 1 as 0. That's all.
Minus 16.
Perfect. So you all saw that, right? So product of eigenvectors, the dot product of two eigenvectors, turn out to be 0, which means they all are orthogonal. Correct? You can see why this is true manually. I mean, there's a small derivation, 2-line derivation basically. But then keep this in mind. What does this signify? Can we open that image matrix? Remember, put an image and write a matrix and it will show you what happens to the image. Can someone open that?
I'll share the link
Yes,
to
sir.
that. Sir.
Sure. Write a symmetric matrix and see what happens. And a non-symmetric matrix and see what happens. What's the difference? Keep it 1, 1 only maybe. Yeah, what do you observe? Replace that 2, 2 by, let's say, 3, 3 or some constant numbers. What do you observe? Do you see the what is that blue and green, red and blue vectors?
That's the eigenvectors.
Yeah, they're the eigenvectors. See, they're putting. Can you vary the vary 0.5, 0.5 to something else and then see what happens?
You moved away. Now they got back.
Yeah. So guys, what does it signify? Play around
I
this.
think
Play around GeoGebra if you want. Okay. Only intuition, nothing else. Tell me how symmetricity is leading to some uniqueness in the transformation.
I think the image is getting stretched and squished along those directions.
If you try 1, 1, 1, 1, 1, 1, 1, then the stuff will be a straight line, I guess. That's where it's going.
Yeah. Yeah.
So,
Vectors, Maria.
yeah, so this stuff is just, the closer the, the values are together of the symmetric matrix, we can see that it's getting squished and squished. If you have, farther values, then it will get stretched, I guess. Put 0.01 on, those two ends, I think it will get stretched that way. Yeah, so it gets stretched.
No, but what is happening when this is not a symmetric matrix?
No, 0.2 on the below also. This is kind of skewed, but if you do 0.2 here also.
So something that I thought of is symmetric matrix also means that like our figure is symmetric. So eigenvectors are actually the direction where the variation is maximum, right? So in this case, when your figure is symmetric, you can obviously see that the variations along perpendicular directions would be the same, right?
Perpendicular to what? Perpendicular
No.
to what?
Eigenvectors like can be thought of as a direction where your variations are high, right? I mean, when you apply the metrics to it, okay.
One thing that I can think of is when the thing is symmetric, the scale of the image doesn't change. So if you can see the image is like this, then this stuff gets tilted like this. Okay, we are
What do you mean by scale?
from this place.
What do you mean by scale, Sriram?
It doesn't get skewed, the what to say, the the dimensions of the image, right? They don't change. The image itself.
Yeah, so we have the diamond shape because the two eigenvectors are perpendicular. Now we have to figure out why are those perpendiculars in case of symmetric matrices.
What I am thinking is that in case of symmetric matrix, the magnitude of both eigenvectors is same, but when non-symmetric matrix, the magnitude is getting different.
Okay, Athara, can you do one thing? Can you
Yes.
take different values for the diagonals and just slowly move towards symmetricity?
Uh,
0.2.
which okay.
No, I meant
Let's take 0.
And I meant that first of all, we must write the original matrix which is representing the image, and then afterwards slowly adjust the values of the matrix such that it becomes symmetric slowly.
Okay, 1001.
Okay, okay. Yeah.
So that we can see what is the pattern which is arising. Okay. As we can see, these two perpendicular lines in the plane itself, right?
Yeah.
And now if we start changing the values, which element is kind of, okay, see, it has sheared rightwards.
Yeah, yeah.
Okay,
And
but we have not changed the diagonal elements, both of the diagonal.
yeah, so, if I change this one, I get a shear in the right direction. And
Yep.
if I like nudge this one, we get a shear in y direction.
Correct.
So if we give it the same shear in both directions,
Both directions.
I think,
Okay.
yeah,
It's getting
both the directions equally. If we share them in both the directions equally, then I think we should get this.
Still the blue and red vectors are perpendicular, but are they in the same plane? Earlier, when it was 1001, they appeared to be in the same plane. When they?
They're in same plane only.
Okay. All. Okay. Yep. Then the same plane.
Yeah.
So as we are kind of changing the value of the diagonal elements, we can see the shear. The first row is kind of shearing it on rightwards, that is along x direction, and the second row diagonal element is kind of shearing it along the y direction.
What do you mean second diagonal element?
Okay, can you guys do one thing?
left.
Can you guys do one thing? I'll give you a list of wishes from my side. Try fulfilling them. First one, your blue and red vectors there, whatever they mean, they should be close to xy axis. Not equal to, but close to xy axis. Get them close. You may want to modify your 1 also there. Do it, no problem.
They are on the
Go
xy
ahead.
axis.
No, you already saw that, no? No. Make it 1 only and make it close to 0. The other points should be 0.1 karo.
Okay.
0.01. That should also be 0.01. Do you see a small modification leads to the vectors going this side, that side?
Oh.
Yeah, play around. 0.01 only. 0.01. What does 0.01 give you? Yeah, how come the image is the same, but the vectors are this side, that side?
Oh. Yeah.
No. What does it mean? It just means that it is not pulling so much. Although direction of pull is this and this, it is not pulling so much. It is pulling slightly only. Okay. If you want to pull more, make it 0.1, 0.1. Right? Make it 10. As a zooming factor also, right? Okay. So what is happening, guys? Well, make it close to x and y axis by hook or crook.
Do 1.1 and 1.1. Try these values once.
I think that would squish it into a line. Kind.
Zoom out.
Okay. Hmm.
Yeah, because its determinant is kind of close to 0. Or both of the vectors are basically nearby.
Can the link be shared on the chat so that I'm not able to?
Yeah, let me do it. Let me share the link.
I think one thing we can observe is that the eigenvalues are, one is the sum of the, the row, one is the, sum of the column. Can you see that?
No, guys, isn't it very easy to find out how to generate that blue and green vector? Isn't it pretty straightforward from your understanding of matrices?
Sir, I guess it should be 0.1 and 0.1, but it is not happening. So
No, figure that out from your understanding of linear algebra, conceptually. What's an eigenvector? Something on which when the matrix acts, you get lambda times that. Just move that red and blue somehow, this side, that side. Okay, move it. Of course, you should meddle with the diagonal elements. It's true. Double point.
You have to
हो गया यहाँ.
increase it.
There's a typo there. No, 0.5 नहीं है, 0.5 हो गया.
Want it close to the x and y axis, I think we have to increase the first diagonal, which is whatever you have in 0.5, you have to get it close to the.
Yeah,
Yes,
it
isn't
is.
it moving towards the x-axis now? Isn't it?
Yeah. So what if we put negative here?
See, the
Maybe.
matrix magnitude should not make any difference. You can always multiply a scalar to the entire matrix.
Yeah, so 1, is it moving closer to the x and y now?
Yeah. So I think if I put a very large number here, it is moving like really close to the
Okay.
xy plane.
Okay. And what happens to the image? Reduce everything by a what happened to the image?
I put a very large number, that's why it disappeared.
Yeah. So what you do is you scale down everything.
Yeah. So this.
No, zoom out. I mean, the mouse, you zoom out. What does the first column represent, guys?
Where I cap.
Where your I cap is going. You are holding the I cap and making that become that. Your I cap basically becomes that. Now your J cap becomes this.
Second.
But that is not, I mean.
Yeah, Srivinay.
I cap, it tells us where I cap is. It tells us where I cap is going. But does that mean that is where it's being stretched? So that should be the eigenvector?
No, it is not. When I cap goes there and J cap goes here. Okay, so let's now switch to GeoGebra. Now is the right time to switch to GeoGebra. Anyways, so two-dimensional GeoGebra.
Yes, sir.
Okay. No, 2-dimension. Sorry.
Oh, okay.
All right. So you create a matrix, maybe 1, 2, symmetric matrix 1, 2, 2, 1. See its application on a vector and move that vector. Let that vector be in your hands. Move that vector.
I think it's better if you define a point and define a vector to that
No,
point. and you can-
A B move hoga na. This also moves,
Yeah,
right?
yeah.
Okay.
Yes.
Yeah. Now, do you see somewhere it meets the line? Correct. We have discussed this before. Somewhere it is meeting a line, and that's what is an eigenvector. Correct.
Yes.
कहाँ पे हो रहा है? नहीं नहीं, यहाँ पे भी मीट हो रहा है. करेक्ट. यहाँ पे हो रहा है, and then दिखाओ.
Y equals to
नहीं.
x.
There is a second quadrant में भी हो रहा है. हाँ, देखो
Yeah,
your
yeah.
side is meeting. Direction
Y
is
equal
negative.
to-
That's all. Eigenvalue is negative.
Y equal to x and minus x.
Yeah.
Okay. Why are these two vectors perpendicular? Make these two vectors very close to each other, let's see, by modifying a matrix. Put anything you want, it needn't be symmetric. Put whatever you want. Yeah, just play around it. Yeah, perfect. Just play around it. Put to some whatever.
They're kind of tending.
It looks like the same.
It is slightly off here.
No, you see, yeah, this is one eigenvector. Other one is
No, this is slightly off, right? So we are not getting it on x is equal to y anymore. We
yeah,
are
it is slightly
getting it
off.
here.
Correct. That's one eigenvector. Other one?
Would be in the second and the fourth quadrant.
See, it is more or less like the previous one. Slightly off, yes.
Hmm.
I want these two eigenvectors to be close to each other. Let's say both of them should be in first quadrant itself. Look at this again and again.
Achha.
I keep repeating the same thing. All these theories emanating from two cross two matrices. Okay. And yeah, that's okay. See, I don't mind what exactly is the slope.
Yeah.
Someone else wants to try? Go ahead. You must do trial and error to get an answer. The answer is actually very fascinating. What happens is when you move this, a small movement results in a huge deflection of that and it comes this side. Try some negative values maybe. You see? Move it around and then show us what's happening. This is resulting in a rotation.
Okay, this is not symmetric or even close
Complex
to symmetric.
eigenvalues.
Yeah.
तो यहाँ पे एक मिला और
Here somewhere.
again still it's perpendicular.
Why are they perpendicular?
No, they're turning out to be perpendicular.
Make it symmetric one, it will be perpendicular.
They're not perpendicular, they're close to being perpendicular.
Yeah.
That's only obvious, no? Your matrices appear close to being symmetric. Okay, will you guys play around? Shall we go ahead? You can in fact get any two vectors. You can give me a matrix, given two vectors, call them eigenvectors. You can have a matrix whose eigenvectors are these. है ना?
Yeah.
Maybe I will be able to do it, but I don't know how.
Yeah, basically you can solve.
Yeah. Like how, meaning why it is happening. Like,
AV
I don't
equals
know.
lambda V.
I don't
AV dash equals lambda dash V dash. That's all. Two vectors. Yeah, Shrivana is saying something?
But I don't know how to how to move them around freely. Like I understand that if I take ij and I see where it is going. So if I say ij such that ij is moving close to each other, it means that there's basically squish. So
Oh,
this
no, no,
direction
no.
will be
IJ moving close to each other means that first column and second column is second column is angle is less than 90, right? That is different. What
No,
we're
but that
talking
is telling
the
me
angle
that
between the
there is-
eigenvectors.
Yeah, but it's squishing the space. So I feel okay, one side, so the direction between them somewhere is going to be an eigenvector.
Okay, let's write that down. Write down the matrix 1, 1 and 1, okay, 1, 2 and 2, 2. 1, 2. Write down these 2 points. So 1, 2, 2, 2 points be likh lo. 1, 2, 2, 2, and then the matrix with columns 1, 2 and 2, 2. Maybe zoom down. Okay, good. So this is the matrix. So this is what Shrivani was trying to say. This matrix sort of pushes your I and J, I cap, J cap, to like this. Okay. And when you look at the image also sort of squishes like this, right? But then the eigenvectors for this, let's compute that. Move that around. Move AV around. Move V around. Yeah, move V around. Everything is right, no? You just need to move V around, that's all.
Yeah. Yeah, so we'll have those two vectors also.
It
Can
only
you show
makes
the
sense,
other-
no? In between only it should be scaling, right? Scaling is in the direction of between in between the mouth.
Now my question would just be that, okay, if I'm able to understand that if I do this kind of thing such that I take a matrix where the I cap and J cap are coming close to each other, I know one of them is going to be along that. Is there a way I can bring the second eigenvector also to be between that, is what I thought. I mean, that would take a step further.
Yeah, no, second will not be inside that. Second will be outside the mouth, as you can see here, right?
So squishing doesn't help. I mean, squishing will have
Yeah,
eigenvectors.
squishing
in
does not
different-
give you the intended whatever eigenvectors will also, if the mouth of the columns is small, the resultant eigenvector's mouth will not be small.
If I make it big, then will that kind of work? If I try to push the I cap and J cap away.
Let's do it. So can you do one thing, Atharva? Make the first column, second column as a variable. That's possible. Create a tuple and write the matrix and take its transpose. Or simply put A comma B and C comma D.
Okay.
I hope this works. A comma B and C comma D, and create the vector A comma B and C comma D. Okay. Now don't worry about this. Now create the vector AB, A comma C and B comma D. And B comma D. I hope delete the free variables A, B, C, D.
It is deleting the matrix also.
You should be able to delete, no?
No. As long as we have A, B, C, D in the matrix or the vectors, if we delete those free variables, it deletes the matrix also.
Okay, write a vector A comma B, just the vector A comma C.
I think we can take these vectors also. We can move them.
You can move them, right? Yeah, take them as the first column and second column. P.
Okay.
Good. And then make it Q. And then write Q above. Whatever. Copy paste this so that.
Just change the Q equal to A comma B. Make it a vector. No, do not delete.
I'm sorry.
That's okay. No.
Create
Okay. Shall I go ahead? I feel like I'm well versed during the.
Sure. Go ahead, Shivani. No problem. You take the transpose, is it?
Yeah. Is it possible to take the transpose?
Yeah, I think you have to write transpose of U.
Yeah, U dot transpose.
Then a transpose of
Transpose of U. Vinay, transpose of U. Transpose is a function. Yeah. Transpose of U.
No, but then this may not work. Because the syntax error, no? You must write in a tabular form. No, right?
Maybe create transpose of U and V separately and then enter that in matrix. It does not allow the composition of functions.
What if I make them as points? I can still move points, right?
Yeah, yeah.
Or I think the last thing we can just do is ABC. Is that okay? I mean, we can change the values of them one by one. So this is okay.
Yes, sir, I got it.
Got it?
Yes, sir. Shall I share?
Yeah.
Yeah, go ahead.
Yes. Yeah, so V and W are the column vectors.
Okay.
So I just basically did V dot I cap, V dot J cap, and W dot I cap, W dot J cap.
Okay. So
And
there should be a way to find eigenvectors also here, no? Check. Nahi. Okay. Is it there? It's not there, no? It's okay. So move the first column, second column, and look at the action on the vector. There are 4 vectors totally. C1, C2, V, and A of V. Okay. Is that right? Atharva, is it clear?
A of P.
A
Yes.
of V.
So blue and pink vector are basically the vectors where we are taking our I cap and J cap, and this is a variable vector.
Why don't you label them? C1, C2,
Yeah.
V, and AV.
No, that's redefining the vector.
I think
Just right click on it and right click on the vector.
On the vector, Atharva.
Yeah, I now this should be right. Yeah. Now it is taking I cap to A1, A2.
Yeah.
Just label them.
Yeah.
Right click on them and show label. Show label.
Okay. C1. C2. A. Yeah. So if we take this,
What you do, scale them up a bit because you have a lot of
Yeah.
labels, right? So you're not able to move them.
See them? Maybe you can zoom up. Scale, you can scale or you can zoom up. Or...
Yeah. I think I made one more mistake here. This should be B1, B2.
No, first column, second column is the same, is it?
No. Yeah. Now this is C1 and C2.
No, I didn't get why is it saying A equals O? Now it is
Yeah,
0, 1, 0.
okay.
Okay, 0, 1 and 1, 0. Okay.
Yeah, this is a column
Column
1.
1 is 1, 0. All right. ठीक.
Yeah.
So we know that when they both, if both I cap and J cap go to the same line, then we know that at that point, the eigenvector, there's only one eigenvector. So,
Yeah.
but we realized that when we try to bring them close, the eigenvectors, one was here and one was in the opposite direction. So bringing them close doesn't make sense. Maybe if you want to show why bringing them close also doesn't. Try to bring them close and see the eigenvectors now.
Yeah. So try all possibilities, make them close, put them into across the quadrants.
Yeah.
Yeah.
This is the
So
first.
this just gives us those same two eigenvectors, one inside and one outside.
Perpendicular, is it? Okay.
Yeah. And
put C1,
what
C2
if
wide open.
we have one here?
Oh, they're getting close.
Yeah, the angle is very small, you see. Now what you do is,
Yeah.
see, the idea of two-dimensional plane is you can even rotate it. Rotate C1, C2, maintain the angle and rotate C1, C2.
Move C1 to the left and C2 up. So what he wants is try to get it closer to X and Y. Or maybe actually the other way.
X and Y, okay.
No. So this happens. If this happens, the eigenvectors are in the first quadrant and the second quadrant. What we want to do is bring the eigenvectors. So that we want to bring the first eigenvector close to the x-axis and the second eigenvector close to y-axis. Right. So you want to rotate towards the right. So
no, let's take up the challenge of putting. Let's make it even more crisp. That we want both the eigenvectors inside first quadrant.
Both eigenvectors. Okay.
For that, if column vectors collides,
there'll be only one eigenvector there.
Yeah, means just in the first and third quadrant now. Then.
No, move P now.
This is sort of similar to the very closed one. When C1, C2 are like really close to each other. This is sort of similar.
What is the angle?
Can you share this on the chat window, the link to this GeoGebra
Yes.
notes?
As they get closer to a line, one of the eigenvectors is moving towards that line, while the other one is like getting squished down completely. That's what I am. Maybe it should not be too far away, not too close. I feel that's where the answer is.
Just bring this C2 to x-axis. You will notice that this, yeah. And now try to move B. Yeah, this.
Take a look at this. I'm is my screen being shared? Is it shared?
Yes, sir.
Yes, sir.
Yes.
Okay. Now look at this. I am moving P. Eigenvector मिला एक, दूसरा भी मिला. Steven, is that right? Eigenvector
sir.
1,
Eigenvector 2.
eigenvector 2. What was the angle?
Both in quadrant one.
Not
Both in
90
first
degree.
quadrant.
Hmm.
So are you getting the hint? What's happening?
After they cross over, why does they feel like they moved away again?
Yes, because even slightest change will have an impact on them.
Now it feels like there's a 90-degree angle.
Okay, so yeah, this beautifully illustrates what's happening. You guys are observing what I'm doing? How do I make AP get back to me very soon? By any chance, can you make P go on a unit circle, Atharva?
I think so. To make a circle as an equation and take a point on that circle and then define a vector to that point.
Okay.
Now we define a point on equation 1. So point EQ1.
Am I editing your file? Is this like resulting in the
it
editing
makes
of your?
your own local code.
Okay, so put P equals something and make it 1 minus of this, is it?
So you will define it by easier way.
Can you help me, Srivinay?
Yes, sir. So can you hear?
Yeah, Srivinay, tell me what should I do here?
Yeah, create a point on EQ1. So new input.
Create a point on EQ1, is it? Oh, okay,
EQ1.
okay. So how do I create that?
point brackets EQ1. Now define a vector to that point. It only moves along the circle, and now you can define the vector along that. So you can make P equal to vector of P. Yeah.
Sir,
And
or
now
else
you
you can just create a slider and edit P to cos T and sin T.
नहीं हो गया ना? But then it should become C1, C2. This B should become C1, C2. Can someone help me? Okay, so guys, instead of C1, C2, I want no, this is all right. Yeah, everything is right. C1, C2 to also be on the unit circle. Okay, perfect. That's what I want. C1, C2 should be on unit circle. And your P also should be on unit circle. That's all I want. Can someone help me?
how would you define the angle of it? Cos theta?
Angle of a?
We can just create a slider and we'll make a point P is equal to cos T and sin T. We can vary T's.
You can either do that or again define 2 points on the circle and make C1 and C2 to that point. Cos T. So can you share the one you created until now so that we can edit over that?
How do I do that? No, because that
Oh, I
is
think-
what our friend had shared.
I can create a new link. Or does that work?
Oh, okay. So I
If
need
you
to
save
share
it
this.
and share. Yeah.
Yeah, save it and share. Okay. Okay, do it and finish it and then share the screen and then do as I said. The point is your C1 is the x-axis, right? C1 is your E1. C2 is your E2. Correct? Let me know once it is done.
This is what you want.
Okay.
P is on the line.
Put C1 to exactly. Yeah. This is the usual identity matrix, right? B is AP. Move C1 a little. Yeah, now move B. Now, isn't this expected? Why?
Yes, sir.
Why? This is also squishing, but then C2 direction remains the same. In C2, you're not doing anything. In C1. Okay, so then now move B. Now move B. Where do you have an eigenvector here? Isn't that expected? It should be along C2 because in the C2 direction only it is not. C2 is becoming C2 only. That indeed is an eigenvector. Right? But where is the other eigenvector? This is the same as C2. Where's the other eigenvector? Now, the other eigenvector is when you move B and B crosses AP. So when will come down? Yeah. It's actually at C2, right? Now get C1 closer to C2. No. Before doing that, you just guess what will happen now. Yeah, move C1 closer to C2. Yeah, move C1 closer to C2. Much closer. Much closer. Now don't move B, but tell me where will you find an eigenvector? Of course, along C2 will be one eigenvector, right? So where will be the other eigenvector as you move B? Don't move B. Wait. Guess. Huh?
No, the other.
Move B. Move. Yeah. Go ahead. See, where is it?
Here is the first one and here is the second one.
Move C1 even more closer. Yeah, the magnitude of C1 is playing its role. Okay. Move C1 really further away, wherein bring it to the last quadrant. Now. Yeah. Now, see, isn't this obvious? You see, when C1, C2 is this, what happens to the image? In the direction of C2, the image remains the same, right? That's what you're saying. C2 is becoming C2, which means eigenvalue 1. In that direction, the push is nothing. Nothing changes in that direction. But your I cap is becoming C1. Okay. So the idea is you take I cap and J cap and move them the way you want and then stretch them in a particular direction. What happens to the image? That stretching tells you the eigenvalue and the direction in which you are stretching tells you the eigenvector. Har ek image ka, when you stretch it using these operations, you will have two directions in which you will be pulling them. Pulling them with a scaling factor. Okay. Now I'll drop a small bomb. I'll quickly go to the nth dimension. You understood, right? There are two ways to see a matrix. One is what's happening to your I cap, J cap. Once you see what's happening to your I cap, J cap, in two directions, it gets pulled. Either you can see the matrix as in this two direction it is getting pulled, or you can see where is I cap, J cap going. Okay? Okay. Now look at this. We're going to look at this. How many of you have seen this before? Okay. This can be a little advanced for today, so I'll stop with a question maybe. Given the data set, let's not forget the big data set that we wrote with several columns, right? That Excel sheet. You're going to do this exercise today, all of you. This is an algorithm to find out the answer for that. What was the question? Remember? What is the Google sheet?
11th column is the linear combination of the first term.
Can someone show me that sheet?
Yes. Should I share the link for that?
Share the sheet itself for a minute. Let's take a minute's break. Once we see that and then look at my notability notes, it'll ring a bell. We've come to a very good stage where algorithmically we can analyze that question. Anyway, so the story so far, you don't worry much about all the geometry that we did. All that we know is matrix I cap, J cap को कुछ कर रहा है. वो होता है आपका C1, C2, right? That is one thing that is clear. When this happens, it gets pulled in a couple of directions. That's what we observed. That's all. It's a very empirical observation. Yeah. Okay. Anyone sharing?
There's a link in the link is in the chat for this spreadsheet.
No, maybe someone can share the file itself, screen itself if possible. Perfect. What was sheet 1?
This is the sheet one, sir.
Yeah, what was sheet 1?
It had 10,000 rows and 11 columns. Each column was representing a particular test, and each row was corresponding to a particular patient.
Okay, the question was about for sheet 1. What was it? Show that nth column we can get done with.
Linear combination of the first 10 columns.
First 10 columns. Okay. What is the sheet 2? What is the question for sheet 2?
So it was the same for sheet 2 as well.
But
and
L was an approximation.
Yeah, and sheet 3 was which columns can you drop in sheet 3?
Which you all are going to worry now about sheet 3. Yeah. What was the answer? Did you guys get any answer for sheet 3? No?
Yes, sir, we got some coefficients.
What? Tarva?
We got some coefficients, and like last two of them were very, very small.
Okay. All right, so I'll now share the screen. So all you do is that's all is the algorithm. Many people just understand this. Now I want to see a difference. Here is where we are hitting we are crossing a big bridge now. We have been walking, traveling on the highway, and we're crossing a big bridge. You will faint and fall in case you don't walk properly, right? Here where, of course, this is the data set is not this. There were long rows, right? Lot of rows and few columns. Correct? So what you do is we can also take it as the transpose of this and make it m cross n. Correct? Or retain n cross m, not a problem, right? What you do is you call this matrix as your A matrix. Take A transpose, which is m cross n, and multiply it with A.
To get a symmetric matrix. Yeah.
You will get a symmetric matrix. And for that symmetric matrix, you will have numpy.linalg.ig, right?
Yes, sir. For eigenvectors, eigenvalues.
Okay. Let that eigenvector matrix be E. This is n cross m. Am I right? What's the dimension of E? This is a little
N
boring,
cross.
guys. Don't worry. I purposefully want to make it boring and give you the intuition slowly. Okay? Let's only look at the boring part of it. What is E? Dimension of E, Srivinay? M cross M. Why? This eigenvector was the eigenvector of this matrix. Okay. Now what you do is put a dot here and take the product of these two matrices. Okay. You will get a n cross m matrix. Correct? N cross m into m cross m. You'll get an n cross m matrix. Now, what you can actually do is, here's the, as we keep calling it, the climax. You can, instead of m, you can take a part of it, which is k. That's all. See, in one page, I have told you the dimensionality reduction algorithm.
So the eigenvalues which are smaller, we can make them 0.
Yeah.
We ignored them.
Yeah.
Yeah, like we did in SVD.
Right.
Yeah. SVD का कहानी थोड़ा अलग था उस तरफ. यहाँ पे बस
Yeah,
हम we are multiplying
PCA.
it with the top class eigenvalues, eigenvectors. What are these k eigenvectors? The eigenvectors corresponding to higher eigenvalues.
Vectors are.
I mean, we did the same thing when that day with the Lana image where we ignored
The
We
smaller
did exactly.
eigenvalues.
Yes. Pause. Very good. We did this with random vectors, no? K random vectors. Now I'm telling you, the best candidates for those random vectors are the eigenvectors of the matrix and its transpose. Now what we will do, guys, is at this point, we will declare our ignorance and say, we'll detect the zone where we are ignorant and backtrack and fill the gap from all the linear algebra that we have learned. Okay? Can you all revise what has happened in this one slide? This is basically memory. This is like tables. When a kid learns 5 tables, it has no clue why 5 tables is used. And randomly you show a clock and see this is the application of 5 tables. Right? It may not even know what is 5 tables. Right? You see this as 5 tables. Memorize it for the time being. We'll backtrack and see in and out of this idea. Can you all revise once whatever I have shown here? Go ahead, Shivana, you want to try?
Yeah. So we had a matrix which was of size n cross m, where m is much lesser than n. N is a large number, and m is a very, like, compared to n, it's a very small number.
M is the large number and N is the small number. The columns are lesser.
Yeah, columns are less. M is small, N is large.
M, yeah. So m, the number of columns is small, and n, the number of rows is large. Right? I mean, we have a lot of patients and we have less details about each patient. That's how you can think. Yeah. So now we wanted to make it symmetric. So, okay, we just took the product of A transpose, we applied A transpose to A, and we saw that the result will be a square matrix, right? Symmetric matrix, right? It's going to be an m cross m matrix. And the eigenvectors of that m cross m matrix, yeah.
What is E? What is E, Srivinay?
It's a matrix with the eigenvectors of A transpose.
Yes.
So Yeah, see, so the eigenvectors for A transpose A, since A transpose A is a square matrix and a symmetric matrix, we know that those eigenvectors will be
Orthogonal.
orthogonal. Exactly. So that's something we saw. We'll have orthogonal eigenvectors. And now we want to take a product, take a product of A and E, right? Why is that useful? I mean, we can reduce, since we know that E somehow holds the value of the directions which are very important. We're saying, okay, we can ignore a few directions, which is nothing but saying making a few eigenvectors, removing a few eigenvectors from that matrix. The ones which have a very low eigenvalue.
Correct. So can we put this to observation? Atharva, do you have just 5 minutes time? In 5 minutes we can wind up. If not, don't
Yes,
worry,
sir.
I'll understand. Do you have?
Yes, sir.
Okay. Can you open Google Sheets?
Yes, sir.
Whatever sheet 1, 2, 3 that I had shared, the same sheet, you open and create a sheet 4. Okay, so what we'll now do is we'll create synthetic data set of a lot of columns that are linearly dependent on the other columns. Okay, anyone here who's very good at Excel?
The Davis Smith sir is there.
Davis Smith is not around today, no?
He's here.
Oh, Davis Smith is here.
Sir, yeah, I'm actually traveling, but I'll be back in room in another 10 minutes.
Oh,
But yeah,
don't worry,
I'm
don't worry.
listening. Yeah.
Don't worry. When we say Davis Smith only. Okay, so what you do is replicate sheet 1 as sheet 4. Click on it and then make copy. Copy to do one thing. Go to file. Go to file. Do a make a copy. Make a copy. Make a copy. Make a copy. Copy and go to this sheet. Okay. In this sheet, simply delete sheet 2 and sheet 3. And sheet 3. Okay. Come to sheet 1. And after blood pressure, which is B, C, D, E, F, G, H, I, J, K, L, retain all the headers. Come to F2. Delete everything. Yes. You can use shift control down arrow. Shift control down arrow. Delete. Yes. Now go up. Control up arrow. Now say F2 is equal to, create your own linear combination of B, C, D, and E. 0.11 of B2 plus.
Times.
Say into.
Times.
Now, why don't you share the screen with Sri Vinay and Chetan so that they can write it for blood glucose, thyroid, liver, and.
Yes.
How do I?
Go to
Just
share.
go to share.
Top
Okay,
right.
Change the from viewer to editor and restrict it to anyone
And
with a link.
meanwhile, you guys type your email ID there. Maybe Ankit, Nishan, Sri Vinay, Maria, Sri
I'll just
Ram.
give anyone with the link, right?
That's a better idea. Yeah.
Just Atharva, change one more thing. Go to that and change the setting from viewer to editor.
Editor. Yeah. Go to viewer.
Yeah.
Bottom right.
Bottom right. Yeah.
Editor.
Just save it. Yeah. And just copy the link.
Post it in the chat window and raise your hand, those who are going to edit the other columns. Ankit, Chetan, Ashik. We need 3 more. Sri Vinay is 4th. 2 more. Others don't read, so that Nishan, raise your hand digitally. Yes, 5. We need 1 more. Okay, Swapnil, go ahead. Ensure that your coefficients add up to 1. 8-3 काम नहीं करेगा. Sum should add up to 1.
Oh, okay.
Point 5 कर लो. D2 plus 0.61, 0.85, 0.15 है ना? No. Correct. 65. Correct. 6535. Correct. You're right. 0.15 Atharva.
Okay.
15 of E3. E2, sorry. E2. Enter. Now copy paste it all everywhere. Control C and then Control C. Control C. I'll tell you technique. Wait, don't do
Control
that.
Shift or down, arrow down. Control Shift down arrow and just paste there.
Paste it. Yeah, exactly. Control Shift down arrow. Yeah.
Control Shift
Down arrow and
Control
paste.
V.
The link on this.
You'll have to copy the formula from there.
No.
Oh my God.
Just do no formula. Just do Control C. That's all. Go to 63.33 and do Control C.
Yeah. Copy the formula there. Control C and Control Shift.
No. Now Control C. Now Control C. That's all. Now come down. Just say Control V.
Yeah.
That's what you should do.
Control Shift or down arrow.
Control Shift down arrow and then Control V.
Yes.
Yeah. Atharva, now check the others if they have done the right thing. Guys, you don't do anything. You only do the first row. The rest Atharva will fill in. Atharva, you just check that it is all, sum is 1. Chetan, maybe you can check that.
1.6.
It is to 1.6.
Yes.
But it's not using, okay. Yeah.
We had to use first 4 columns, right?
Correct.
Yeah.
Everyone should use first 4 columns only.
Yeah.
Actually, you can use any, use
Yes.
anything. It doesn't matter. Mathematically, it shouldn't matter.
Yes. Sir. I think we'll need one more here. Serum creating.
No, I've done it. I just wanted to check it before to copy this.
Okay.
Yeah, it's correct. Just simply copy it.
Yeah.
Chetan, you meanwhile create sheet. Okay, wait. Create sheet 2. Yeah, is everything over, guys?
Yes, sir.
Formatting tick kar lo, Chetan.
Let me handle that thing. So
Yeah. Everything done, no? Now, yeah. Chetan, just copy B2. Come to B2. Shift control right arrow. And shift control down arrow, Chetan. Which means you are just saving the data in sheet 2, correct? Yeah. Now, Atharva, you come to sheet 2. Let's see whether Chetan has copy pasted properly. Done, Chetan?
Somebody else has done something. So
I have only arranged the format, nothing more. Just
no,
like
there is an error in one column. Somebody,
okay, that I
yeah,
don't. I just included this around.
maybe you can undo that and let me just paste the data. Can you undo that?
I did only this borders and circles, no formula change. So it will not be visible at my end.
Somebody else did that then.
Do one thing, Chetan. You remove all the editing rights now. Chetan or Atharva, one of you. And you do what I just now said.
I don't know how to remove
Chetan, you can
editing.
instruct Atharva on what needs to be done.
ಅಥವಾ just copy the data from there. Just go to sheet 1, go to A2, sorry, B2, go to B2, Control Shift right arrow, Control Shift down arrow, Control C, go to sheet 2 and Control V. Just paste the data there. Yeah. Perfect. It will
How
come.
come,
It will come.
how come only 4 columns?
It will
We need
come.
all
It
columns,
takes time. It takes time for data to load.
I didn't paste anything.
No, now delete everything.
Chetan,
Control A, delete.
Chetan, are you creating a copy of sheet 1 data itself?
Pardon?
Are you creating the copy of
So
sheet?
now every data has been copied. Just wait for 2-3 seconds. It will get updated. From my side, I'm able to see every single value.
Okay.
Yeah.
Okay, just delete the first column. You copied the serial numbers as well.
No, wait. I think Ashik has done it.
Yeah. From my end, it is visible for all columns.
In that case, what you do is maybe you can remove the sharing, Atharva. Just so that if Ashik has done it, in some time it will get. No, not this sharing. Sharing of the Google Sheet.
You can just refresh it. Refresh it also reflect all the changes.
Yeah, and just go to the settings and change from editor to viewer.
Yeah, actually, there are many data, like a lot of data. That is why it is lagging a lot.
Yeah. 10,000 into some.
Yeah, just save it.
Yes.
Yeah, I guess it is visible.
No,
Yeah.
serial number B I have. We should get rid of that.
Just delete the first column. Delete the entire column. Yeah.
It is not data. It is formula based at this moment. All the sheet 2 data.
Yeah. So if you delete that first column now, it goes away.
No.
Yeah.
No, why?
Someone has used that in the formula.
Because it has been copied along with the formula. That is why.
Atharva.
Okay, so we'll just keep this empty column.
Yeah, let's keep it this way, or else while copying we should only do Control C and
paste.
Paste without
only.
formula. Yeah,
paste
exactly.
values only.
Yeah.
Do one thing. Yeah, this will not be. Do one thing. Atharva, just remove the editing rights for everyone now, for a moment.
Yes, sir.
That's already removed.
Yeah, they are being removed.
Go to share. A viewer is done. No, okay, it's done. Yes. Now close this. Close this. Click on it and Control A, delete. Delete everything basically in sheet 2. No, go to sheet 1 and repeat this exercise. But just don't paste it. Just copy, and I'll tell you where. Right click and copy. Copy this.
Yeah.
Go to sheet 2 and go to A1 and don't paste it, but go to paste, right click, paste special, values only.
Values only.
Hmm.
Control Shift V.
Yeah, all the
Yeah.
columns have come, guys. Can you just cross check once?
Yes, sir. They're there.
Now, Atharva, please download this as comma separated values. Go to file, download CSV,
Yes, sir.
and create an NumPy matrix out of this. So,
Uh,
and take its transpose, find the
Yes.
eigenvector, and then multiply and then see what you get.
Hmm.
Maybe you can share it with everyone so that all of you can do it. What should you get now,
yes,
guys?
I'll share.
Theoretically, you saw what happened. Only some columns are important. Other columns are dependent on these columns. That is not known to us. Right? Are you all with me?
Yes.
Um,
Hello, can you share the link?
yeah. Just a second.
No, guys, you all can do it too. The sheet is available for all of you. It is not in editable format. It's in viewable format. You can also go there and then download
Sir,
it.
the sheet 2 is not visible there.
It will take some time for it to come, I guess.
Chetan, just refresh it. It will.
Oh, refreshed it multiple times. It's not.
Yeah, it's taking a long time to download. Yeah, even for me.
Actually, it's writing saving at Atharva's end. When it's done,
Oh God, yeah, it is still
Yeah,
saving.
yeah,
Now
right,
it's
right.
done.
Yeah.
Now
Done,
it's done.
done.
Now it's
Yeah, now it's come. Now it's come.
For some reason, everything feels very slow at my end. Even uploading. I was uploading the CSV file for this in
Okay,
the chat.
okay.
Okay, guys, everything is done for me. I can share the file with you guys. There you go. It's a CSV file. Okay, just download this 482 and cross-check and let me know if it's the right file. CSV file, don't open it as Excel. Let's just let it be as it is. It's all comma separated values. Let me just show you that. Do you see?
Yes, sir.
Okay, I zoomed in and it all went out. Okay, so this is the file. Now, Atharva, use Git Copilot. You can
Yes,
share
sir.
the screen and use Git Copilot. Okay, write down the details. Rename the file as data.txt. I mean, yeah. Perfect. Now go back to trial.py.
Yeah.
Okay. Open the file by name, data.txt in the current directory. The current directory. This contains comma separated values of 10 columns of data. How many columns? Can someone count?
11, I think.
Yeah, 11.
11 columns, sir.
11
And
columns.
10,000 rows. 10,000 rows.
And 10,000 rows. Yeah. No, that's all. 10 columns is understood. No, 10 columns. 10 columns and 10,000 rows भी लिखते हैं. हाँ, ठीक है, correct. 10,000 भी लिख लो and 10,000 rows. Is it really 10,000 rows, guys?
Yes, sir, exactly 10,000 rows.
10,000. Okay.
Yeah.
Create a matrix A of dimension 10,000 cross 11 using this data. बस इतना करते हैं हम. Let's see if Copilot can do this. I somehow think it's too complicated for it to do it. Let's see.
No, sir, it does that. I've done
Does
this.
okay, you're
Yeah.
more confident. Good.
So which version this Copilot uses for calculating? Like 3.5 or what?
No, this is not
Oh,
GPT.
no.
This is Copilot. No, this is Codex
Oh, okay. Okay.
from Git.
I think 10,000 cross 11.
1,000 cross 11 with the data in the file. That's all. Correct. You're right. NumPy matrix. NumPy. ठीक है.
Sir, I did it. I did it on Polar.
Oh, is it? You want to show?
I just
Okay, let's
used,
see. Maybe otherwise also close. If this doesn't work,
yeah.
we'll switch to Sri Vinay's console. Create a matrix X of dimension. Oh, no, not required. Not required. सब कुछ ठीक है. ये बस इतना ही दिखाओ. Just show this. You are right. A dot shape. Undo. Just go ahead. Yes, perfect.
It's going to take some time.
It will not take some time. It's just from 10,000 cross 11. It's a. Oh, what happened?
No.
Open data.txt.
Contain no.
It should print the dimension of the data.
Oh
sir,
no,
right?
data.txt कुछ नहीं है. क्यों? Is it the right
I think
directory?
because yeah.
ls start.txt. Okay. You did MV, is it?
Yeah.
Maybe
But
move
MV just renames it.
move the file once again.
Data.txt. Okay. How do I like again move the file here only?
Yeah, you should download the file once again. See, data.txt में कुछ नहीं है ना? Empty है ना?
Yeah, cat data should show something. It's not showing anything.
Okay, CP.
Yeah, data. So,
Yeah, enter. Okay, क्या है?
yeah.
Rename
Now
it
I
to
have
data.csv. Not txt, data.csv.
.csv.
And modify this in your Python file. By name data.csv ही करके पूरा पहले से कर लो. Comment ऊपर first line.
I think you'll have to change the function as well. np.load txt might.
Load
yeah.
txt, yeah, exactly. So just go back and then exactly. First line में make it data.csv. Vim expert, huh? Good, you're all doing the search through slash.
And then once it's a pandas data frame, you can do to NumPy.
Yeah.
So that's,
You try it. In case you can, then you can show us. Otherwise, Srivina, you can show us.
Yeah, I did exactly what the investment said. I read it as a CS, I mean, read it as a data frame. And then I did A is equal to D of the NumPy.
Very good.
and then I print the sheet.
Okay.
I got the eigenvalues.
Okay.
So these are the eigenvalues.
Okay.
This is a very high value. 2, 3 high values, 4 high values, 5 high values, and then the next is very, very, very small.
Correct. Correct. That's right. No, that's what we did, right? How did we create? First 6 columns were high. First 5 were high. You're right.
Yeah.
Correct.
1, 2, 3, 4, 5. Yeah.
Yeah. First 5 were high. Exactly.
Other 6. You drop the first, last 6 and retain the first 5.
Last one is high as well. So I think last one is the high, one of the highest.
No, it can't be. It's minus.
Oh, sorry. Yeah, right.
Okay, minus. Right.
Last one is highest, is it?
No. That's the smallest
No,
value.
no.
It generally is in the descending order always.
Yeah.
Now for this we need Atharva from this point onwards. It's easy using Copilot to. 4, 6. What were the eigenvalues? Tell us.
4 power 9. 4 into 10 power 9, 6 into 10 power 7, 1 into 10 power 7, 8 into 10 power 6, 9 into 10 power 6. And then it's minus 1 to the power into 10 to the power minus 10. Can you see?
Show us the screen. That's easier. That way. Okay, 4. Basically, it's 4, no? 4 and then 6 and then 1,
8,
then 8, and then 9, and then what is it? Minus 1.09, is it?
1.77 to e to the power minus 8.
Oh, e to the power of minus, that means it's 0. Yeah. These are all zeros, right?
Yeah.
The rest are zeros. Perfect. You must only consider then the first 5 eigenvectors. Okay, good. Now this is enough. This observation should be enough right now. Now, what will A into E give us right now, according to what we have written?
Is E, sir?
E is the eigenvector. So all the vectors, eigenvectors as column.
Yeah, maybe someone can explain briefly so that Devasmith is in the
Okay. So what we did was we had a synthetic data set of 11 columns. We took that data set as CSV file, we loaded that in Python. We took A transpose times A to get a symmetric matrix, and we found out the eigenvalues for that and eigenvectors for that. We were looking at the eigenvalues and eigenvectors for A transpose A.
Okay, got it. So that is the okay, got it. Yeah, thanks.
Okay, so here are 2 questions. Question number 1 is, why were the eigenvalues so low for some columns, for some eigenvectors, and for some eigenvectors it was really high? First question. Second question is, tell me what's in the red bracket here, red rectangle here. And when we consider K, when you multiply A with the eigenvectors in particular, what will you get in return?
So when we multiply the matrix with the eigenvectors, the direction doesn't change. I think it remains. And it's so
This
we'll
gets
always,
scaled by the eigenvalue.
Yeah. So you get lambda I basically.
Okay, so at this point, I will leave it to you people. As I said, what we'll do is, of course, you guys discuss, continue to discuss. We are going to backtrack now from this problem. We're going to discuss everything that we have understood so far in linear algebra. We're going to go till vectors. We're going to go till dependency. We're going to go till linear transformations, right? And go, see, we did this right now. We have reached this stage right now. Now we're going to go back and then come once again and then halt here. Okay, things will be perfect for you people then. All right. Also, what we will discuss in the upcoming hours, meaning tomorrow, day after, is how do you actually find E? See, algorithmically, you're studying data science. How exactly do you get this E? You're using a NumPy package right now. What is happening within that is also important. In fact, it is very easily computable. E is very easy to compute. Especially for real world matrices, it's so trivial. We'll discuss more. Now, on to you people. Two things to discuss. Why were the eigenvalues so low for few vectors and so high for some eigenvectors? What does it denote? Number one. Number two, what do you get if you multiply this A, n cross m matrix with E, m cross k matrix, where k is the first 5, while you drop the... right?
Eigenvalues.
Correct. Go ahead.
So one thing is, it's like squeezing the balloon, right? So if the volume or determinant of the matrix is constant, so essentially by this process, the determinant, a product of all the eigenvalues is equal to the determinant of the matrix. So by that process, when some of the larger eigenvalues take most of the value, then by default, it has to take power from all the ones. So it's kind of winner takes all. So because the product is constant, that's the constraint. So it's like a balloon, right? If I squeeze, so the other part is big, then the other one has to be small, so that the overall remains the same, right? So that's the analogy I would see, right?
Yeah, go on. You guys discuss. If you
That's
didn't understand,
life.
maybe you can ask David Smith to explain more. I'll make a move at this point.
I'm not sure when you said like the product is being dominated, right? So even a very small value, like say 0.0005, even that will dominate the product somehow, right? It will pull down the product a lot.
No, one thing that
so think about, let's say ABC. Yeah, go ahead.
Yeah. One thing that David Smith G said was that determinant is constant, first thing. Then he built on that. Can you go from there, sir?
Yeah, determinant is for a given matrix, determinant is given. I mean, it's fixed, right? For a given matrix A, right? So when we are decomposing the A transpose A, so it is essentially giving us all the eigenvalues of A transpose A. So when we multiply all the eigenvalues, so we'll get that constant number. So let's say if we are given a problem that I have to multiply 5 numbers and the product is, let's say, 1, right? So if my first number is 5, I already know another number has to be 1 by 5. So that way, product, if it is 2 numbers, it is 3 numbers, if it is 5 and 4, the third number has to be 1 by 20, right? If you make it 4 numbers, let's say 5, 4, and 3, we already know the fourth one has to be 1 by 5 into 4 into 3, because the product has to be 1. I mean, of course, we're choosing intentionally 1, so it's very trivial for us, right? So it is C. You can replace it with a constant C. Then, so that is what it is. Like, so if once we have bigger eigenvalues, means it's like what we call as in real life, right? Yin and yang, right? So when you have a large lambda, then it has to have a very small lambda.
Right. And a small x, if it's large and smaller than x.
So you look at that 10 to the minus 8 we are seeing means plus, so you will see. So obviously once it becomes very, very small, then you will see those minus. So essentially it is to counteract the large values, that's all. Yeah. Again, this is again a geometric property. I give the example of balloon, like, the air is constant inside. So it's like an equivalent of determinant, right? Squeeze it means it's small, other one is big, right? So it is satisfying the volume constant. Similarly, if you think that way, a matrix, because of that restriction, It is almost expected that high value of lambda will be associated with other conjugate pair. I'm not saying conjugate, but in math we always see that, right? So because of the constant.
A high value of lambda. So a high eigenvalue represents like kind of how much that direction it's being it's being like that direction is important. In that direction, we are being
yeah. So let's say it's a let's say our space is a three-dimensional object, potato, right? Let's say we have a elliptical potato, right? Imagine that. So it's like an ellipse or ellipsoid, right? So if we are asked to calculate in what direction is the maximum variance explained, right? So you'd see always we studied in school, right? In a major axis, minor axis. So it is kind of same, isn't it? Right. So which is like if I align all my vectors in that direction, then the variance is kind of maximum, right? So that's the intuition that I developed when I was reading linear algebra. That every matrix, when we decompose to these eigenvalues and eigenvectors, essentially what it is doing is it's giving us the directions where this maximum information or variance is contained, right? So the one thing is they're not orthogonal, they're just eigenvectors where there is maximum information. That's all they're doing, right? Special cases when it is orthogonal and Gram-Schmidt, that's like a special case, right? That's but in principle they may not be orthogonal because we're talking about basis and all that. So wanted to clarify that point.
So when we get A transpose A, we have a symmetric matrix. Then our eigenvectors for that would be orthogonal.
Perpendicular.
No, but let's build on first. First we have a symmetric matrix that is A transpose A. And now what we are doing is we are finding eigenvectors. Yeah.
For that.
Eigenvectors is something when we provide it input to a matrix like AX, it will give lambda times X.
Lambda times?
Means a scale version of X itself.
Fine.
Yeah, means so if that is happening, then here why are eigenvectors orthogonal? First point. I
Not
don't
just a scaled version. Direction will also change, no?
Yeah, we saw that they were two direction maximum like for 2D space.
That was a 2x2 matrix, right?
Yeah.
So if you're thinking about a football, it's spherical, then it will be orthogonal. But if you're thinking about, let's say, a rugby ball, right, that ellipsoid, right, then you can clearly see, there may not be, or some irregular shape like ellipsoid, right? So, so when things are natural like spherical, then you will think it will be like orthogonal. But when it is non-spherical, then you won't expect orthogonality.
So it's not given that eigenvector, there can be certain angles between eigenvectors.
Yes.
Okay.
So just like basis vector span. Yeah.
So why did you say that it has to be like a shape? Because when we saw, okay, I don't think you were there, but we were trying to look at the matrix and, we were seeing that maybe I'm talking to Chetan and others who were there. Remember when we first tried to look at changing the diagonal entry symmetrically, we were looking at symmetric matrices. The shape was always different. It was not always a proper sphere. I mean, it was an ellipse like this, or that also worked, right? Even those had orthogonal
eigenvectors.
Am I not following?
So I think
Yeah,
there
I
is the spectral theorem on symmetric matrices. There is something lovely about symmetric matrices because A transpose A is symmetric. Hence, we get some special properties, right? Otherwise, if it is just A,
rectangular matrix.
Particularly for square symmetric matrices, when we decompose, I think I don't know if it was covered or not. Sorry, I'm kind of coming in between. I don't know how much has been covered, but there's a beautiful spectral theorem that gets covered. I don't know if it has been covered or not. So
no, sir, it has not been.
Let's write all the things and build on what we learned today.
Yeah. Let's start with the very basics. I just want to understand first When we say eigenvectors and eigenvalues, what do they mean? Then let's build on the part where we take A transpose A and start from there.
Want to get a
Yeah,
stab.
so yeah, yeah, so something like what Devaswit sir, sorry, I got your name wrong. Yeah, said is like, yeah, the basic idea of eigenvectors is that, yeah, that would be the direction where variance is high, right? So
No,
if a
I
shape,
understood the theoretical part. I understood the theoretical part. I want to get a geometrical intuition for that. When we say that, okay, the variance is high, I want to see I want to understand
yeah,
that
we actually
geometrically.
did that one day when we took a circle and we made an ellipse and we saw that we did that one day actually.
Yeah, we said that circle will becoming elliptical, but at that point we were not able to dive into it. And now we have some ideas, so let's build on
Yeah,
first.
let's build on that. Yeah.
First, let's build on this symmetric matrix.
What
And
are eigenvalues? What are eigenvectors? Just input and output vectors, isn't it? At the end of the day,
I think
in
generally,
general, in general.
what I learned is
Yes.
when you are doing some linear transformations, right? Either it will change the direction, and sometimes it will also change the magnitude, right? So change in direction can be called as rotation, some sense, right? Change of magnitude is called as scale transformation, right? So typically, when
Right.
you take a vector and apply a matrix as an operation, matrix is a function, right? So you're essentially doing a linear transformation. The output will also be a vector, but in some different direction and with a different magnitude, right? So this is typically what happens. However, when we multiply with some special matrix containing ... then the direction does not change.
Eigenvectors.
Correct. Right. So it's beautiful, right? So we can actually, in fact, the other day, I think 2 days back, Chetan was, almost, we kind of seen that kind of movie, but in a different light, which is, we can take, let's a vector 1, 2, 3. I mean, vector from a matrix, and then we multiply, and every time we'll see the direction will change, magnitude will change, the resultant. But there are certain special case we'll come up with where the direction will not change. Now, one must think like why it is not changing. That's some, and then we'll understand. So there's a proper way of understanding, what it actually does. So as we discussed, matrix is a function, and also it's should be also seen as what it does to the unit
Input
basis.
vectors.
Yeah. So if we start with a very simplistic mind, 1, 0, 0, 1, what it does, right? So essentially, if I take a 1, 1, 0, 0, 1 and I multiply with another matrix, so what it tells you, okay, how much is my scale and how much I'm rotating, right? So every time, but if I come up with some other matrix where the 1, 0 and x-axis and y-axis is not changing, then you know that that is a special case. So again, we are thinking from fundamental
what
first principle, right?
eigenvectors are, right? Yeah, all from first principles. Yeah, so I think Davis Smith also put it very well, and I think we should all be clear that eigenvectors are special, right? In a sense that in the two things that happen to it during linear transformations, only one of it happens. Rotation, your rotation happens. Okay, wow. Okay, can you hear me?
Yes, yes.
Yeah, perfect.
Good.
Yeah. So it only scales up the vector, right? Given an eigenvector to the matrix, you take the eigenvector and input it to the matrix, it only scales the vector, right? I think that is the first thing that we see. And even geometrically, we can see that, right? When we were trying different inputs, right? Along the GeoGebra plot, when we were going around that circle, when we were moving P around that circle, there were certain points where it ended up only Yeah, it ended up only scaling over it, right?
Right, in the same direction, but scaling it, right?
Or different direction, even just opposite directions, it was scaling. That is negative
Yeah, that
eigenvalue.
was another eigenvector we were getting.
Yeah,
Right.
so we got two eigenvectors for a 2x2 matrix.
So
right?
for that, so can we say that it's not the matrix that has that speciality, but those special vectors that are special, which when inputted to the matrix are just scaled up or down.
So you saw the property of the first column and second column, right?
Mhm.
The first column of the matrix is just telling you where I cap is
I
going
cap
to,
will go.
and second column is telling you where J cap is going to. So that's a property that you encapsulated within that matrix.
Right.
The other property that you could have used is the property of the eigenvectors to tell what the matrix is. I mean, maybe it doesn't tell you what the matrix does completely, but it is telling you in which direction I'm stretching, right? That is also a property of the matrix. Yes, it is only special for eigenvectors, but
No, I guess it is very important
Associates the
to
matrix and the vectors together.
exactly the eigenvectors are a product of the matrix, right? It is specific to that matrix. So that's what I'm trying to say. Just like how Maria put it.
Yeah.
How we saw I cap and J cap, I mean, what we saw the first column and second column as, we should also think of eigenvectors as properties to that matrix, which follow such a certain, like a, maybe say like a rule or like have a nice
Yeah,
property in them.
that's what I meant. That it's not the matrix that's the special there, that's special thing there. It's those vectors that are special when inputted to a particular matrix. They're just scaled up or down.
They are like
So
more a signature of a matrix.
no, just a second, Shivam. So what? What?
No, the
Shivam?
particular matrix doesn't exist, right? Given a
No, no.
matrix, you have eigenvectors. Those eigenvectors only work for that.
But yeah, that's what I meant. For that particular matrix, only those eigenvectors will work, right? That's
It's
what I
like a
meant
pair,
with for
not
that.
two.
Yeah, a pair. If you input that to
Yes.
some other matrix, it's not going to work out. It will not be the same. That's what I meant for with particular matrix. Okay.
They are like signature of a matrix. Like, they act like a blueprint for the matrix itself. You can see that they carries the most essential part of the matrix information that is carried. You can.
What do you mean when you say most important part of the matrix information?
I mean to say that there is a way for you to construct the matrix. If you know some, the constant values, you can reconstruct the matrix from
Okay,
this
if I
blueprint
have
that is given
if I have eigenvectors, can I construct the matrix?
with the known scalar. Yes, at least you can alpha into the matrix. You can do that, but
I think,
directly the
yeah,
matrix.
the main idea is that
you can construct the matrix out of a vector.
Not only one vector, all the eigenvectors together. There is not only one vector for a matrix, right? Like 3x3 matrix will have.
Okay, you are talking about eigenvectors, right?
Yeah.
Can some start on writing something like
Yeah.
because the only idea till now I get it. Eigenvalues of eigenvectors, what it essentially does is scaling certain things. But beyond that, we need to put more thought.
Go ahead. I think you've joined with the right number. Go ahead.
Yeah, like something that I thought of, like we actually wanted to understand why when the matrix is symmetric, why is the eigenvectors come out to be perpendicular, right?
Oh no.
So like
That would be jumping too far. We haven't even properly understood what eigenvectors, eigenvalues are, what they're doing when we're inputting them. Understanding why they are perpendicular, when they are perpendicular, would be just jumping 10 steps ahead right now. And
yeah,
also
I
one
mean,
more thing,
we discussed
what
that it would scale, right? And another idea is that, like, if you have an object that's like an image or something that's represented as a matrix, uh, wherever
I want to
maybe not
understand
getting.
what's happening in that image. It's not the image part that's special. I want to understand what the vectors are doing there in that image. I think that's image just is just the representation. It just explains
I
you
think
when
even my understanding is not well, but like maybe Davis Smith sir can try this out. Like, why do you say that? Like, we associate like maximum information along the direction of the eigenvector, right? Why do we actually say that? I mean, can someone actually elaborate on that? Like, because I don't think my understanding is that good.
just a second. Also, sir put two questions there. Can someone also write down those two questions that sir asked us to focus on? Yeah, go ahead, Devaswin, sir. You're saying something.
See, I think every matrix. No, basically just a observation that every matrix will have. I mean, every matrix is unique, but for once the matrix is given, the information is constant. Our idea is to find out how the information is contained there, right? So this is where when we try to decompose and all that, we find some special vectors, and when we apply those, multiply those special vectors to that, then it will not change direction. Why? Because that is what we have to figure out.
No, I think, yeah, I mean, maybe just to get the intuition of why that might have the most variance, I have like maybe just the same example, but think of it in this way. Okay. The eigenvector is just
When we
getting
say
scaled.
variance, variance with respect to what?
Data.
So
The
okay,
data
itself.
maybe
spread of the
data, yeah, data.
like how the vectors
See,
are spread
How is
across that area, right? That's
not
what is
not vectors? How data is spread across the Cartesian plane or any space?
Oh no, I get it, but I understand variance. I'm asking in terms of vectors what that would mean.
Yeah, so if I have a space where I'm okay, that's okay.
Where most of the data is kind of clustered. That is the thing, I guess. Clustering of data.
so
We are
think
dealing
about
with a clustering of data.
think about a 2 by 2 matrix, right? So we are starting with a 0, 1, 1, 0. So when you look at that, it's a perfect unit square, right? So we can say it's a unit area. Now that's kind of how what is ideal or fundamental unit block, if you will, right? Now if somebody gives us a matrix 3, 1 and 1, 5, something like that, why are we saying determinant is 14? What does it actually mean? When we say 3, 1, 1, 5, so we say, okay, 3 AD minus BC, what it actually means?
We actually discussed this one day. I mean, it's like the area between it's a measure of the area between the two vectors, right?
It's the scale.
We can say that it's just area found by the bases, the new bases, like here 3, 1 and 1, 5. The rectangle
Would that be correct to
area
say that?
that is covered.
Why not? I mean, it is right.
So when we understand
You guys
when we
remember
understand
that
in so if it is not square, when you're finding an area of a square, you multiply, right? It's like, AB is mod of A, mod of B, and cosine is 1. I mean, literally, when the angle is 90 degrees, that's what it is, what we studied in math, right? When you're square of square, then you straight multiply, right? But if it is an angle, like a rhombus, then it is not straight multiplication. So essentially, you take the one side, the other side, you kind of project and then only take the angle to make it 90. Like, this is fundamental what we learned in school without any complex math, right? It's intuitive, right? We all eat barfi, right? It's not a square, right? It's like some kind of, right? So same way, right? So when we are seeing a matrix like this, which is not symmetric, not orthogonal, then when we find the determinant, it has to have some special properties. Now, when it is an angle, if somebody says we want to find some directions where you can see when the object, there's a length and breadth, right? Length is higher, breadth is smaller. You fundamentally know that if I want to find the area, the length is bigger and breadth is, right? So right? So similarly, if it is an angle, you know naturally there will be certain things will be bigger, other things that will be smaller. That's the intuition we should have, right? So this is why when you decompose, you'll always have a big brother, you'll have a small brother. And if the big brother is very big, the smaller brother has to be smaller because our area or land is constant. That at least we should understand. Then after that, we'll say, okay, if I multiply, I rotate, I scale, then doesn't matter what I do, the direction doesn't change. Then those are all special cases, right? Most of the time they will do something, but in center special circumstances, the direction will not change. So those are all eigenvectors, right? And in fact, we did that in GeoGebra. It was probably done here also. I'm talking about 2 years back. So we did it and it rotated, but in one case it will not change.
Multiply.
Yeah,
Yes.
we were doing that earlier today. We were doing the same earlier today. Can we get that draft? Does someone have that link? Vinay, you were sharing your screen, right? When do you have that link?
I have it.
Let me establish here. You can share it.
This one, right?
Yeah. So what are my input vectors here to the matrix?
Wait, let me change it a bit. Yeah. P is your input. These are the two columns of your matrix, and this is your output.
Okay.
AP is your output.
Mm-hmm.
So this is a particular eigenvector. And does it cross again? It crosses. Okay, it crosses here once.
We found another one in the second quadrant as well, right? Oh, no, that was the same.
One thing we can observe is if it's an Rn space, then at maximum we can have n eigenvectors.
N power n space.
Yeah.
N cross n.
No. Means n, this dimension of columns.
N-dimensional space.
Yeah, at maximum we can have that. But we still saw that in one of the cases, we were, even if we are in R2, we were having only one single eigenvector. A particular case.
If you take a vector 1, 2, and 2, 4. Basically, the second vector is basically nothing but just 2 times the first vector. So when you plot them, the first vector is this little, second one is so it's in the same direction. Well, it is giving you the illusion it is R2, but it is indeed R1, right?
Yeah.
This is where again related to that 10 question, right? If we find another column 3 is just a straight multiple of another column, so essentially it is adding no extra information, right? So from that perspective, even if our matrix could be n by n, what we should think of is kind of, again, if rank was discussed, right? So how many, if none of the columns can be expressed as a linear combination of other columns, then we know that,
that's a full rank matrix.
Yeah.
And we will have n eigenvalues as well, eigenvectors as well.
Yes. So it's a full rank matrix, basically, right?
So rank has to do with eigenvectors.
In fact, the other way around, right?
Yeah.
Depending on the rank, you will find the. But I guess they are related. But yes.
If we kind of ignore dependency or independency,
Vinay, what is the intuition that we are trying to get from here? I get when we are changing the matrix and the input, we are getting different eigenvalues, different eigenvectors, I meant. But what was the intuition part that we were trying to get from this?
No, do not change both of them simultaneously. Change both of them one by one. Either change the matrix or change the input.
I know. So there were three things that we did, right? First, we saw that for symmetric matrix, if I make the matrix symmetric, right? I think I can do it here. Here is a symmetric matrix, or I don't know where else I can do it. 1 0.
1 0 0 1.
Maybe here also it will be symmetric. I need this.
Just make them 90 degree.
This is close to symmetric, right? At this point, the eigenvectors, okay. I don't know, rotation, right?
It's just rotating. There are no eigenvectors for this.
No, I think what he wanted us to understand is that if you take a symmetric matrix, the first thing we had to observe was that the eigenvectors are perpendicular, right? And that was, I think, shown better in this image, right? When we tried to change this values, we saw that the eigenvectors are perpendicular, right? Then here he wanted us to see that, by changing the matrix, the eigenvectors change, and you can, like, what he wanted us to say that given a matrix, there is only one set of eigenvectors, right? So
One second, Srivina, if you can go back to that image thing. There we saw that when we were kind of changing the diagonal value of, for example, there are two diagonal values, one value in row 1 and another value in row 2. When we are going to change the first row 1 diagonal value, it is going to skew in the x direction.
Yeah.
And then it is going to skew in the y direction.
Yeah, this is just pulling
So
along the x direction. Yeah.
X direction, and then y in the y direction if we are going to change that eigenvalue.
Can
Sorry,
you change the
eigenvalue.
other one as well? Can you change the other one as well and make the first one 0?
Yeah.
Okay, in the y direction. Okay.
I forgot the question. I'll ask it.
Now when you're doing symmetric, you're actually sharing it in both the directions together, in the x direction and the y direction.
Correct. Equally.
Equally.
Yeah.
And in a way, you're squishing it down. So, like Devasmith sir was earlier talking about that potato, right? Elliptical potato. So now you're squishing it down when you have a symmetric matrix by sharing it in both y and x direction.
For that, it had to be symmetric.
Yeah, correct.
This is what you're talking about, right? Like,
so that means this one has been stretched
a lot.
Right.
So it's like, we all, the best thing is you take atta, right? Make a stretch, right? So you're creating an object, so you can clearly see it's traced in that direction.
It stretched a lot in the red direction and very less. I mean, it's actually come down in this direction, negatively scale down, right?
So if anybody has done physics or strength of material, or most of you probably would have done engineering first degree. So please think of strength of material or stress and strain diagram. You have actually learned it. Nobody told you that this is what you're learning at that time, right? So you think of a metal, and then you actually have, putting and then putting pressure, right?
The necking happens and all.
So what you call is shear, stress, and create strain, right? So you'll see, the direction in which it will be, and then the strain will be exactly orthogonal to the stress and strain diagram. So if you actually, it has been actually everything we are learning and did in the past, nobody told us that. And then even after we learn this, we will still not understand that we actually knew it. So we think they are two fundamentally different objects. No, they are the same. We just don't see that similarity, right? So
this is altogether a different perspective you just gave us. I never thought it like that. I just treated it as just another graph and remember it like this only.
Yes. stress strain diagram. So why we talk about it is something that you can actually physically see, because the math is taught as, like some 1, 5, 5, 10, you don't appreciate that, right? So when you take a metal object, put it on the machine and actually apply force, you will see how many Newton, then you actually see it, right? Then you can see where it is cracking, right? So you can see it, feel it,
Then
right? So
the necking and all.
yes.
It
And it
is
all
in the horizontal direction. If the force is in the vertical direction, the necking is in horizontal direction.
and funny enough, they use the word principle, stress strain diagram, right? So it's not funny why that word principle is used among all the words in English. Right?
Mm.
Yeah.
So in this thing, only the red arrow eigenvector is of importance, high importance.
Yes.
The
No,
other can be.
other one is of importance as well.
No,
Why not
not that
important?
much, because that
Both
is
are important.
small. No, look, they are important, yeah, but relatively, if we are speaking, then the scaling is being done along the red only, no?
No, the negative scaling is being done there, I guess.
So that 1.9 is that angle 45 degree, right? The red one, and the blue
I
one
think
is
this, sir, isn't this what you meant when you said if one of the eigenvectors is very big, the other one automatically goes small?
Yes.
So if we have one, if we have sharing in one direction, just like we are having sharing in this direction of this red eigenvector, in the other direction, the direction of the other eigenvector, the sharing will be less compared to this. The sharing, the eigenvalue for that eigenvector will be less.
No,
Direction would be different. That's why that we are saying 90 degree, not necessarily values.
what's
No,
the
no,
bond
no.
between eigenvector and eigenvalue? Means eigenvector I understand, but
Eigenvector gives you the direction, and eigenvalue gives you the magnitude of how much sharing will happen in that direction.
Correct.
Yeah.
So when I said that the eigenvalue will be small for the blue eigenvector, is because can you see the sharing is mostly happening along the red
What about
eigenvector.
excusing? What about
The,
excusing?
so we can say like it's vector. We can say it as some unit directional vector.
See,
And
you
eigenvalue.
say squeeze is along the blue vector only, na? Chetan.
And
yeah,
that thing I get it. What I wanted to confirm is eigenvector is something like a unit directional vector times the eigenvalue. Is it?
Correct.
Yeah. So here, because stretching is occurring majorly along the red thing.
okay, just a second.
And
Eigenvector
excusing
sense,
is
we are
simultaneously
magnitude and
happening.
Okay, I want to just come to that point that Ankit mentioned that eigenvectors are unit vectors with eigenvalues. Would that be correct if we say that?
Of course, why not? If it is not
I
separately
was also
mentioned,
thinking
though.
about that because
Not alpha times a unit vector, though, but you can always, kind of divide it by its magnitude and find the
Oh, you can always do that, but
Before today's class, I don't know anything about eigenvalues and vectors. I haven't studied.
I'm also saying
no,
intuitively
same.
only.
I haven't studied it either. I
Not
don't know
my-
either. That's why I posed that question.
It's better to not know and learn it from scratch in this way. Wait, I'll ask you
I
guys one
mean,
thing.
yeah,
I'll ask you guys one thing. Now, you said that, okay, red has a high eigenvalue and there it's touching.
Right.
Right? And blue, Dishan says, okay, why is blue also not important? That's where it's squeezing, right? He's right? But now, if I ask you, if I want to express my data, where is my data now? Where is my data? Is it more along the red axis or is it more along the blue axis?
More
Red
along
axis.
the red axis, right? I mean,
Isn't
that
what
if
we
idea.
meant by
no, if we
radians?
jump to the dimensionality reduction, yeah, I am getting the intuition for that, but I just want to, yeah.
But most, do you agree that most of the vectors that was on this entire R2 plane
Is
is
along a red line.
now closer towards the red line,
Mm-hmm.
right? It's very easily, it's like it's all squished towards the red line, right? I'm not saying anything about dimensionality reduction, right? So where is most of the data preserved?
Along
Think
a red
about
line.
it. Think about it.
The larger eigenvalue, towards the eigenvector with larger eigenvalue, right?
That
Because
means where it
every
is stretched
point,
more,
yeah,
stretched
because
more.
every point that which was on the line along the eigenvector, it stayed in that line and it just got stretched. The other ones came closer to the other. I mean, the other ones got squished closer to it, right? Think about it. Other points would have come like this, but this point would have just got like this. The number of points along that line is like still the same. It's like the most of the vectors which were inside that line stayed
They
along
got
that line.
scaled up.
They stayed along that line. So that's what they meant by high variance along that, you know, that eigenvector. Think about it. When you
Like this,
squish it,
this is actually the better way to understand eigenvectors. Like the other way, if you just look at it online, you'll just know that it's scaled, but then you just know that it's that, but you don't get any idea of why it's important.
I wasn't looking online. This is my first time looking at these.
No. I
You were
had
the
this
only
as
one
part of
doing
my
it.
course.
Yeah,
I
I know.
wasn't looking at it online. I had it as part of my course. Like I had to look up eigenvectors before I learned it formally too. Like, so I mean, you won't understand much. Like this idea that more information or like what Srivani said is like the better way to understand it than that just that it gets scaled.
So what is the significance of this blue line, Srivana?
after all the data which is there in that direction, if I want to explain the data better, the only other direction I can explain the data is better is this direction. Because the transformation in that, think about it. Because from where you squished it,
okay,
first most data will be
to
along this.
restore the information back. That would be
Yes.
the direction. Fine.
Exactly. The other direction
The
which would have the least squishing, all the squishing along this side would have been like lot, right? Because it goes inside towards the line a lot, right? Higher
Okay,
magnitude vectors, what happens to them? They come closer to the red vector. They all move closer. The ones near the origin, they'll move only little because their magnitude is so low. Their movement will be very little compared to the ones which are far away from the origin. Think about it like a
So
point.
if there are two eigenvalues, if there are two eigenvectors given a matrix, so one of them is going to be the red one, fine, the one along which the data is kind of aligned,
highest value, yeah,
highest values, and another vector, eigenvector, would be the one along which there will be minimum loss of data, fine, when of course restoring it. Excuse
Even
me.
the
What
first
do you
vector
mean
is
by
doing the same
minimum
thing,
loss of
right?
data?
Yeah.
But
Variance is more.
we can avoid this
Variance would be less
term.
there.
We can avoid this
So
term.
here, think about it. So
Ultimately, we can restore it.
before this, let's say you have data point, and let's say you're using x and y axis. How do you represent the data? With the x coordinate and y coordinate, right? So you know, to define a data properly, you need two things: x coordinate and y coordinate, right? And we did some magic. Let's say we are saying, okay, you know what? We are going to do some what you studied in math to change of basis, right? We decided to change. No. I'm not going to use x-axis and y-axis to define my coordinate system. I'll still use the coordinate system, but we'll do it different. I will now say my new x-axis is that red line.
The red eigenvector, okay.
Which is 45-degree angle to the original x. But now original x is gone. I erase my x and y axis. Now I might define new axis as red as my x and blue as my new y. Now, can you represent all the data points using two coordinate system? The answer is yes, right? How many units, how many steps I'll go in the red direction and how many steps I have to go in the blue direction to define my point, isn't it?
Yeah.
Now, what we are saying is, here is a catch. If I decide to represent my data using only one coordinate, not two coordinates, that means I'll basically say my y coordinate is 0, x coordinate, I mean, it doesn't exist. So basically I define all my points as only x coordinate.
Single dimensional.
That will be okay. I will have some error. What is that error?
The loss of the
where the point is versus where the point when it is projected to that red line.
right.
That's it.
That is exactly.
We are
That's
dropping
where I
the
wanted to go after this year, right? Perfect. That's what I was saying. So once you understand most of the data is there,
So this
then
is,
think about it.
this is, there cannot be a better explanation of dimensionality reduction. How the two-dimensional data got reduced to one-dimensional data, just by changing the basis, or to say by rotating the axis.
Yeah.
This is awesome, Lewis Smith. Thank you very much.
Yeah. So now R10, the problem that Sir gave, right? I was in the car that time. R10 is now going to R5.
But I missed the last part. What did you say about that projection thing? I missed that.
So projection meaning what? Like, so when you say object is 5,3 and I'm approximating that with 5,0. So what does that mean? So let's say I give you a point 5,3, which is using x-axis and y-axis. That means I have to take 5 steps in the x-axis direction and 3 steps in the y-axis direction, right?
Fine.
Now suddenly say, no, you are only allowed to use only one axis. So what would you do? You're forced to define that point as 5, 0.
5,
Yeah,
0.
right.
Yes.
So what is the relationship between 5,3 and 5,0? 5,0 is the projection of 5,3 on x-axis. That's it.
But instead of going along using x-axis, y-axis, we realize most of our data is more towards the red line.
That's the
natural. So even if you drop the y-axis, we are not losing much there.
Correct.
Drop the blue axis.
Blue axis.
Yeah, y-axis. We have changed the basis, right? So our red has become our new x-axis and blue has become our y-axis. And even if we drop that blue axis there, with the y-axis there, you're not losing much. Since our data is concentrated towards our red or x-axis.
So can we infer that this blue axis is just for kind of reference?
Well, I mean, you'll still lose value. You'll still lose value. If you're okay with losing some value, then that's a good decision, right? So, for example, typically we keep our frame of reference fixed, like x and y, and then look at the data. But if we look at the data, tell its story, it will tell its natural axis that exists, which happens to be the red and blue. It has nothing to do with our original x and y. This is kind of very generic for all data sets. But when I am looking at the data set, which is contained in A, it has its own natural axis. And if we allow it to express itself, it will tell the story. Okay, my axis is a northeast angle this. What we here we have 45 degree northeast angle, right? The other one is actually, the blue axis, which is northwest. Typically, we always do, north, east, west. That's kind of traditional way of doing it. We call it orthogonal basis vector. Then in math too, we studied. It's still okay if we rotate, change a basis. I'm doing a linear map. I'm going from here to there, all that song and dance, right? But ultimately, I'm not doing anything. Basically, who told you X should be this and Y, right? I ask a kid, you take this X and Y, that's it. Somebody rotated the graph. Nothing really changed, right? It's just our frame of reference and what I call as north or east. So same thing is happening here, right? So that is basically how we represent the data in a multi-dimensional coordinate system. That's first point. The second thing is what happens when we are allowing it to express itself in natural coordinate system, which are not orthogonal, by the way. Because it is symmetric, it is orthogonal. In real sense, it will not be. Then you will say, wait a second. Why I need to take a tuple of size 10 to describe a point when I am okay with by taking 5 tuple and the point I describe is very close to the original point. I'm okay with that error. But I now will take almost half the space to describe my data. I don't need 10 tuple of size 10, but rather tuple of size 5 to express my data. And that's a wonderful thing because here in the toy problem that Sir gave us, 10, 5. In real life, it will be million will get compressed to 100. Magic. Then you are talking about, if you're talking about doing matrix inverse, which is order n cube, other one is practically impossible to do it to something now certainly feasible. That's the magic, because why we are spending so much of time and energy to do dimension reduction is there are certain problems which cannot be solved even with so much of memory and computation available, because it's just impossible, because they're order n cube, right? Matrix inversion is order n cube. Matrix multiplication is order n cube. If you look at it, how many multiplications you're doing, right? It's if your number of elements is n, you look at the number of computation, it is n to the power cube. And you ask anybody.
Yeah, I wanted to ask something like even eigen decomposition is order of n cube, right? Do you know why it comes out that way? I mean,
machine learning. That is why if you follow the standard algorithms, yes. So this is where there are certain clever people who came up with smart way of doing it. Even matrix inversion is also order n cube. Then it will take humongous amount of time. But there are
yeah,
smart.
there are steps like they make it order of d cube instead of n cube. Like yeah, like that's what I learned. But like why? How does it actually come to be order of? Like if it's a d cross d matrix, then how does it actually come out to be? Like I don't get the logic. Like it's just given that it's order of d cube or whatever it is. Like
I think let's park it for now. I think we'll take step by step, right? But point is
yeah,
what
I just asked it in between. You can continue
yeah,
with what you said, like
yeah.
because
So the
you
whole
seem to be
idea.
pretty knowledgeable in it, so I just asked. Yeah,
Yeah.
that's it.
So the idea of dimension reduction is what is the motivation? Why we are doing it, right? Because sometimes when the problem becomes very difficult to solve, we are not looking for a perfect answer in real life, right? We are not looking for a perfect answer. We are looking for an answer which is 95, 96% accurate. Similarly, when you have you cannot have a solution to a problem versus an approximate solution to the problem, you'll go with the second option, right? Same way we study for the exam, right? We want to score 100, but you have got only 5 hours left. So what do? You only study the important chapters. So those intrinsically, we do all those activities in our daily lives, right? How do you know what is important? Your definition of eigenvalues, what is more likely to come in exam, right? Important concepts, right? We all do that, right? In real life. Except that, if we are representing our textbook in a matrix form, then essentially what we're doing is following the text, which is in those red direction, and ignoring the superficial concept, which are in the blue direction, because there's a time constraint, right? So same way. Okay, so I think we understood, at least hopefully, that what is the eigenvector and what is eigenvalue very intuitively without going through any math, right? We all knew is if we apply that, then if a vector is in that direction, it will not change. So we know that that is a special vector, right? That at least you've already discussed in the past. I was not there, but so those are all eigenvectors and they are unit, let's say, then the magnitude is basically expressed as lambda, or what we call as eigenvalues, right? So okay, so I think that, so what is the second question that we want to discuss? Eigenvalue, eigenvectors.
Not sure. What was the second question?
So there was 2 or 3 questions. Somebody was saying, I don't.
Yeah, sir posed two questions. I've forgotten what those two questions were. So one of them, yeah.
I don't know if this was the second question, but something we had to infer eventually. I mean, I don't know
Can
if
you take a
it's
look at the notability part link there?
You will also share this GeoGebra thing, the circle one.
Sure, sure.
yeah, like for a symmetric matrix, is that the second question? Why they're
Why the
perpendicular?
eigenvectors are perpendicular? Yeah. I think that will be the next question, as you said.
Can you scroll down further?
See, only thing I can say intuitively, I don't have, we are not talking about defining spectral theorem and all that. The point is, if I am thinking of representing all the point inside a football, which is spherical object, right? Intuitively, I know that, you need three fundamental directions, and they will be of equal importance, right? Symmetricity, what it means is all directions are kind of there, right? So there is symmetry, there is balance, right? So that tells us that what when I decompose, I will probably get something balanced, which is like, and when you say orthogonal, meaning what? I'm actually not trying to kind of again, it is not about magnitude, but at least direction wise, right? It is there is no dependency, right? So think of this, right? So when there are two angles, they're not independent, right? Because what do we mean by that? The geometrical, I'll say, if I take two vectors, if I take a torchlight, which is 90-degree angle to one vector, there should be no shadow, right? That's when I know they're independent, right? Because if
Yeah,
I
so
got
no
vector,
projection, right?
yeah, so essentially, right? Because you will get only a point, right? So I'll use the physical example of taking a torchlight, which is kind of putting it on top of the. So you have a vector A and then B, but I take the torchlight which is orthogonal to A and try to put it on B. So I'll get a shadow. If I get a shadow which is greater than 0, means there is some dependency. But if
Some
I get a
projection will
dot, if I get a dot, they are orthogonal and there is no dependence. So essentially, we always say orthogonality implies independence, right? So, and we can physically demonstrate in a lab or whatever it is, right? We can visualize it at least, right? So similarly, when we are talking about symmetric, right? Now let's ignore the magnitude part, right? If I kind of ignore that part, only focus on the direction part, right? Then we know that there is balance, right? So this is where I would say, without going through any math, I'm only talking about intuition, right? So this is where, so what object comes to your mind, like a spherical object or a circle in 2 dimension, football in a 3 dimension. We cannot imagine 4 dimensions, but things where if I ignore the magnitude, they are symmetric objects, right? And then when you when you try to find natural direction in the data of those kind of objects.
So, I mean, even in the example that you mentioned of a sphere, like, then yeah, the natural question, like, I get your point why we take the orthogonal vectors, because they would always be independent. But you can take any pairs of two orthogonal vectors and they would retain the same amount of information, right? Like, in that sense. So in when you have a spherical object, so how like, in that
Okay, I
case,
lost you there. I lost you there. You'll have
no,
to elaborate a bit more.
yeah, no, I think my question was a bit vague too. Like, yeah. So basically, yeah, we associate, eigenvectors with the direction that has maximum information along it, right? So when we take a sphere, we have a lot of possibilities for orthogonal vectors, right? So how do we actually choose the two in the case of a sphere? Because you use that example, I just want to ask that.
Yeah, I think it's hitting it back. I think, yeah, if you think of the transformation, then obviously the magnitude also plays a role. Since sphere doesn't have a magnitude, it's like saying 1001, right? It's like saying this.
Unit sphere,
Yeah,
basically
unit sphere, right?
Yeah.
So in this case, you think that, okay, the eigenvectors are just it's not being stretched in any direction. So the eigenvectors could just be any two orthogonal vectors, like you said, right? It just could
The
be any two
basis
directions.
vectors are as well.
Yeah.
And if this object is a rectangular object, instead of keep asking where, like, whatever that is, I think it's a 2 by 2, right? In this grid, right?
Right.
If you take a 3 by 2, do you think we'll get orthogonal?
3 by 2.
Yeah. I mean, 6 by 4 rather, right? Because it's a 4 by 4 right now, right?
I didn't understand actually.
So this image, if you look at it, it's a grid system, right? So the origin is at the center, and we have got 2 to the left and 2 to the right. So essentially the length and the height is basically 4 by 4 grid, right? The entire
Yeah,
is 4 by 4,
the
right?
entire information, yeah.
Do you understand it is also symmetric object here?
Yeah, this is a symmetric object here.
Yeah,
So,
it's
so
actually
if you make it 4 by 6, also it's symmetric. Is that what you mean? I mean, it would be similar. Like if you cut it into half, you'll get two equal halves. In that sense, it's symmetric, right? I mean, is that what we mean when we say? I mean, symmetric.
So now let's decompose. Let's see what's going on. Yeah.
Even then, you'll get perpendicular. Yeah.
0, 0 means, so don't make it 0, make it something else. Right? So yeah.
Now it is not symmetric, this matrix, but it's still no, it's symmetric. Yeah,
It is symmetric. Your xij equal to
yeah,
vi,
it's symmetric.
right?
Yeah.
So by definition, A transpose A will be, symmetric. So again, that's a special case, right? So when that special matrix is decomposed, then you get orthogonal. But if you artificially make, 0.5 as 0.9, let's say, right? One of them. Right. Now, do you get the red and blue 90-degree now?
No, we don't.
Okay, make it to like a, 0.9 is still there. Make it 2. Right. The more and more you deviate from that, then you would start seeing the red and blue not being 90-degree. The more you deviate, the angle will be even more and more between those two.
100, yeah, okay, yeah.
Oh, at one point it's getting almost a straight line.
Yeah. So what you found there was also interesting. Like when you make it 100, so what it means is that guy is dominating the entire space, right? That tells you that, so here is a special case where one element is dominating. I can define everything in one dimension. Others don't matter.
No, I feel this is not a special case. This is what happens in most
most
real world examples. Yeah.
One vector or a few columns dominate the entire.
So you go to corporate world, there are a few bullies. You go to the class, there will be 10 students or 5 students will consume 80%. So these are all real life cases, right? So if you're collecting data, that's what you would see.
Yeah, there was this one question like when we take the eigenvectors, do we like normalize them when we write it down? Because like you can change the values and the like lambda x, you can make it lambda by 2 and 2x, right? Then also the product will be lambda x. So like what do we actually use to uniquely identify them? Are they always normalized?
There are special cases. If you go to diploma level in machine learning foundation, what they do is you find it and then you project it to the unit sphere. Why? Because you're doing learning rate and you want to, you're doing machine learning, right? What you're trying to do is you're trying to fit a line through the data or a hyperplane through the data. So you start with a random hyperplane. Then what happens? You'll have a lot of errors. Then you find the error, take a derivative with respect to all the weights, and then kind of start making changes, right? So this is where you would see that when you're doing that, what is a good direction to take the next step. So that is where you will normalize it. So essentially, you're bringing it back to the unit sphere, because imagine you are at a point and it's like a crossroad of your life and you take a step. What is the best step in the direction, right? If you're looking at a sphere, you got so many possibilities. So you want to take the step in the direction which maximizes learning, minimizes error. So you'll see that. Don't worry. Let's keep the suspense until you take machine learning foundation.
Minimizes money from
I
pocket.
am doing that now. Like I am doing machine learning foundations.
All right. So then you will encounter it in week 4 or 5. What is a good direction? I don't know if the cow example, cow is there at 30, 40. I mean, maybe they would have changed the Video I took it like almost a year back. So there's a cow at 30-40 and it can graze, move in a circle. So it's so natural, right? Yeah, that's what the video talked about.
But yeah, I think what's special about the symmetric matrix is that we realize we're pulling along the, so when I'm just changing this, we were kind of pulling along that direction, right? Or like we were
Yeah, it
stretching along
gets
that direction.
elongated along that direction. So when we say that they're orthogonal, it means it also means that the size should be, yeah.
Okay.
No,
So small dose of statistics, because we are talking about linear algebra, let's just put a little droplets, which is there is something called when you got two random variables, x1 and x2, they have all their own distribution. Then there is something called a variance covariance. That matrix, when you're representing
always
variance
symmetric.
covariance, that also happens to be symmetric matrix, by the way.
Yeah, yeah.
You're studied in stats too. All those things will basically converge. After a while, you realize whether you're studying statistics, probability, linear algebra, machine learning, everything all will converge. So we are just coming from different directions. Then we are coming to the
Yeah,
origin.
in PCA they do use the notation of a covariance matrix, like, yeah, to understand it clearly. And they show, I mean, all these properties, they don't actually explain or give us an intuitive idea of why the eigenvectors are perpendicular. They just say that because it's a symmetric matrix, the eigenvectors are perpendicular. You don't really know why, or like you don't think that much, to be honest. Yeah.
Yeah, yeah. It takes time. We didn't get it in day one, right? So most of this learning happened after the coursework, not before. At least for me personally.
Well,
So
yeah, that
if
happens.
I knew all this in MLF, of course, I did okay in MLF, but most of the learning happened. Oh, now it makes sense, right? Exam, quiz one, quiz two, exam, everything is over.
Exactly, it's always the case.
Right. So it's one of those irony of life, right? You learn everything after the exam. You don't get any credit for that, but it's okay.
Yeah.
As long as your utility function in life, like what you study in BDM, is not to score marks but to learn, then it's okay. You'll end up as a happy person. But your goal is to only get GPA, then maybe you need to mug up, get the correct answer, then you understand and develop the intuition later on. So it's better to learn it fundamentally from first principle, then it's okay.
Even you were saying something about like how you actually understood.
Vectors. Okay, no, okay, not the vectors this time. This time is the connection.
What?
Couldn't hear you. Yeah.
Your connection
Yeah,
is bad.
sorry. Yeah. Am I audible now?
Yeah.
Yep. Yep.
Yeah, you were saying something about how you understood that like the vectors have to be the eigenvectors have to be perpendicular, right? You were saying something in between.
Yeah, I think so. This is just saying how much to stretch along the x direction, and this is saying how much to stretch along the y direction, right? And if both of them are being stretched along the same way, they would obviously be stretched in, like, if I'm stretching this way and you're stretching this way, it's like, yeah, I'm always going to be stuck in that 90-degree angle. If I'm going to always stretch equally, right? If I try to stretch in different directions, and yeah.
Okay, you go to Domino's or Pizza Hut, right? Look at the dough. What the guy does?
Stretch it. Right. So I don't know if you've seen that they made the pizza. So they'll put it there and then stretch it out.
And you'll see he'll not stretch a lot in one direction.
Yeah.
Kind of. So we all do these things in real life. We just have to somehow find humor, and then you'll understand that it has to be understood through movies, food, sports.
Right.
But even for this case, when you are stretching, the red vector is not along this stretch thing, like where maximum the stretching is being done. That thing we are only observe when uh, uh, means maximum when maximum data converges along the red axis, means the red arrow. Only at that particular time we see that thing, no?
Yeah. So in other words, what we're saying is here the image tells us, we can visually see where it is stretched, because the key postin, we can see that clearly. In that red direction is where it got stretched more compared to the blue direction. It's very clearly evident here, right? Because we can read and we can visualize, right? This is what the image actually helps us to visualize what is happening. In other cases, it's difficult, right? So so that means we call red vector as lambda 1 and blue vector as lambda 2, right? I mean, or x1 or x2 rather in our notation, right? That's what probably x1 or x2. Then my lambda 1 will be corresponding to x1 and lambda 2 will be corresponding to the blue one, right? So lambda 1 will be the highest and
Eigenvalue.
right, largest, and the second largest will be the corresponding to the blue vector.
Yeah.
So this is what we'll see. And then if these two are almost equally stretched, you will see lambda 1 and lambda 2.
Okay. Am I don't know. I'm getting some intuition here that when we were doing that sheet thing, we could have taken we could have checked the eigenvalues for that, and I think that's what we did, right? We checked the eigenvalues for that and saw that which ones are contributing the most, and dropped the ones which weren't. And it made sense to do that there because the difference was big between the eigenvalues there. If it wasn't big, then it doesn't make sense to drop those. I think that would be the answer to that question that we were trying to do that day, of finding the basis for the matrix to figure out which column should we drop.
Yeah,
That's
yeah, I
I
had
think
a doubt in what we did for that, like with the data. So yeah, how did we actually compute the eigenvalues? Like, I didn't get that part. Because
we used we didn't use the algorithm. We used a Python function for that. Linalg dot ig for that.
yeah, but
To calculate.
the whole data, like with the 10,000 rows and the 10 columns was our metrics, and we found the eigenvalues corresponding to that. Is that what we
No,
did?
no, 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 not for that. We did A transpose A and found the eigenvalues corresponding to A transpose A.
Because that
Then
would be symmetric. Okay, okay.
that would be symmetric. That would be symmetric. Then find the eigenvalues for that, and then see if it even makes sense to drop some columns or not. Corresponding to the
But yeah, but how are the oh yeah, it's an n cross n. No, no,
yeah,
no.
right.
It's going to be an sorry, it
If
was going
it's
to
an
depend on
M
the number of columns. Yeah,
If
yeah,
it's an
okay.
M cross N matrix, if it's an M cross N matrix, your A transpose will be M cross M, right?
Yeah, yeah, yeah.
Yeah, same thing. So, and that's going to be same dimension as your eigenvectors, right?
But we like is no, yeah, we found the eigenvalues, but why is it that those eigenvalues actually correspond to
Just a
the
second.
direction of the like the first column or the okay, like we don't know which direction it corresponds to, do we? Like, isn't that the direction which contributes the most? Isn't that the idea? So when we take A transpose A, like how can we say that the first largest eigenvalue corresponded to the first column? I didn't get that part.
Wait. Can you repeat that, Maria?
Yeah, I mean, generally we associate like when we have a pair of lots of eigenvalues, the larger eigenvalue contributes the more information. Like we have more information in that direction.
Yeah, we
So
saw
here
that
we have
as well, right? In the photo when we were seeing that the picture was sharing in one particular direction, the eigenvalue was greater. So if you see here the red eigenvector, the sharing is more in that direction, and you look at the eigenvalue for that, it's
Yeah. But
3.5.
in our case, we had a data set which was consisting of 11 columns.
Correct.
But but we only found out the eigenvalues, and we said that the largest eigenvalue was like, how did you understand that the direction of that corresponds to that eigenvalue was that of the first column? Like, how did you get to that conclusion?
Oh, we got it gives us in the same order, right? If I'm not mistaken.
Yeah,
But
so
that's
what we did was like a bottom-up approach, right? Instead of trying to find the eigenvectors of that 11 A cross A transpose A, what we thought was, okay, we know it has to lie in the space of that column space, right? It has to lie in that column space, right? So we try to take one vector and we try to see, okay, if I have to have the first column, I can just add the column. Like I just need them to be independent. And I know they're independent when they're orthogonal, and they're easy to work with when they're orthogonal, right? Because if I take the dot product between them, it's just 0. So if I do multiply them, A transpose A, I will get a diagonal matrix, right?
Yeah.
Maybe
you'll get
Not
a
the diagonal matrix, the symmetric matrix. Diagonal matrix will have all the entries 0 except the diagonals. So symmetric matrix, when you do A transpose A, you get a symmetric matrix.
if you have an orthogonal matrix, won't you have a diagonal matrix as the output if you take an orthogonal matrix and do an A transpose A?
Yeah, in that case.
Because if I take a row, that row will have a value more than 0 for only if it is dot product with itself, which will be its magnitude. That will have the diagonal element. And if I do the dot product with anything else, we know it's orthogonal. So the dot product is going to be 0.
So if A consists of orthogonal vectors, A transpose A would be a diagonal matrix. Is that
Yes.
okay?
That's why we want a orthogonal. See, that is one idea. Why we are taking orthogonal. Orthogonal guarantees independence, which is one important thing we need. We want to have the independent vector along that. And we know that there can be many independent vectors along in that column space, right? Or the linear combination of those two, first column and second column, when we're trying to take the second column. But like instead of taking the second column, we'll take the vector which is orthogonal to this first vector, right? And then the third, fourth, fifth. So we're just trying to cover that space first. And once we cover that space, it's much easier to represent the points. Yeah. So I don't think the first column is the highest eigenvalue. Sorry, I think, that's what you tried to say, right? Why? How do we know the first column is the one with the highest eigenvalue?
Yeah, which contributes the most because.
Yeah, we're not doing that. What we're doing is we're taking a direction and we're saying, okay, this is one direction. The other directions that the other values can be in has to be on it or should be covered by the linear combination of it with the orthogonal vector.
But
because that will
one more
increase the
thing,
dimension.
One more
Yeah.
thing. When we calculated the eigen values for A transpose A using Python, right? We got a matrix for that. We have that, right? This is in descending order. Is it in descending order or is it?
Yeah, it's in descending order. You always write the larger eigenvalues
So how
first.
do we figure out that which columns do these values correspond to?
You can
Yeah,
print
I mean that's what.
eigenvectors also.
Okay. So can you also print eigenvectors?
Yeah, I think I have to restart and I have to upload the data. All the data is there.
Yeah, the sheet is there. There's an option to run all, right? Run all cells here.
Yeah,
It's already saved the previous one, so I'm just printing it. So this is the first column corresponding to the first eigenvector. This one. This is the first column. This is the second column. This is the third column. And respective eigenvectors 1, 2, 3.
Yeah, I didn't get you actually. Like,
But these are in descending order, right? How do we know that our first three columns are corresponding to the contributing the most?
No, that's how we usually write them. So you take the eigenvector which has the most eigenvalue to be your first. I mean, this you usually do that. I'm not sure how. I think that's just how NumPy calculates it and gives it to us. Maybe we can always get a set of eigenvectors and the corresponding lambda value for it and arrange it in descending order in both the ways, right? Descending order according to the eigenvalue.
I'm just
Yeah, I didn't understand. Can you switch to the collab again? Like, I didn't understand. Like, there are lots of values. Right? It's supposed to be a single direction, right?
This is one vector. Vector is telling you which direction, right?
Oh, yeah, there are 11 components to that. Yeah, yeah, right.
dimension of that is 11.
Yeah.
Yeah, yeah. I mean, as for some reason, I was thinking like, yeah, it was supposed to be 2. Yeah,
And
that's
the
why.
first eigenvalue maps to that. But how do I know which column this eigenvector corresponds to?
Yeah, yeah, that's what. I mean, we by default took the notation that the first eigenvalue is to the first column.
No, I don't think we did that. We
I'm a
just
little confused.
we only concluded that we can only drop the columns which has the lowest eigenvalues corresponding to.
Yeah, yeah,
But we
yeah.
didn't
Okay.
cover that part. That how do we figure out that which values correspond to which column in the data set? We didn't actually talk about that.
column wise. Okay. I mean, okay. I'm
We know that the eigenvectors are perpendicular, right?
Vectors, Maria, vectors.
Oh. Hello, am I audible now?
Yes, ma'am.
Very
Okay.
loud.
There was a wake up call.
Yeah, yeah.
Sorry. Yeah. Yeah, okay. Yes. Yeah, like I'm just giggling. Yeah. Yeah. So we know that the eigenvectors are perpendicular, right? So I think this is where we have to apply we have to apply Gram-Schmidt thing and find out the orthogonal basis thing. So after we find that out, we know E1 corresponds to V1 and E2 corresponds to V2, right? I mean that's a step I think in that sense also it would come out eventually that the first column is the first, right?
I have a doubt. Are you guys confused about how these two are mapped, which is this value and this value is mapped, or are you trying to find
No,
out?
the actual matrix.
See the first so in the second matrix that we have, the first entry, this entry with 11 elements is one eigenvector with 11 dimension, right? And the first value, that is 4.015, corresponds to that eigenvector. Clear with that part. But how do we figure out that which column does this eigenvector value pair corresponds to?
Yeah, yeah.
I'll
I
give
think
you I'll give you a
yeah, you
simple
can
answer
say.
to that. Yeah, I'll give you a very simple answer to that. At first, what is your space? You're going to take one vector. You took the first column, right? There's a reason why you took any random column. You could have taken the first column, 11th column, 10th column, 9th column, 8th column, because in the end, what you want to do is want to find some place where you can define all of them, right? Okay, I took the first column. I realized I need the direction. Or else I cannot define that vector, right? I need the direction. So I added the direction. I added that as my first vector, right? And then I have a certain eigenvalue for it. I don't know if it is the highest. I'm not saying it is the highest value, right? I'm just saying it is one of these values for this, right? I see the second eigenvector. I see the second column, right? And now I find whether if it is in the space or not, right? If it is in the space, I don't even need to go in that direction anymore, right? If it is in the space, I don't have to. I can just ignore that column. But usually it happens to be in the outside the space, but very little deviation from that space. That's what we mean by you can approximate and all that stuff. I'll talk about that later. But what I'm saying is, okay, I take the second vector. Say that happens to be an important vector. Then obviously I will add that us column ka the vector which is perpendicular to the initial vector. I will add it, right? And that will maybe have a higher value. So I will append it in such a way that comes on top. I mean, I don't know if it makes sense. You can just
so you're saying that
you're building it in a different way. Instead of trying to build it from top to bottom, you're populating it, and as you see new columns, you realize, okay, this was really important. I saw it late, but I can just append it in first, saying, okay, this is a high eigenvector with a high eigenvalue. Like it's saying, I can put it into the eigenvector space at any point, right? I can put it at any point, and according to its eigenvalue, I can order it. That's all I'm saying. So taking the first one is just thinking about, okay, if I had only one vector, I knew I had that direction. I have to go that direction to reach that vector. If I need the second direction, the second orthogonal vector to that first vector will give me the direction. How much in that direction will come from the eigenvalue, right? Corresponding to that. So in the end, you will just get 11 eigenvectors. I mean, you will just get 11 vectors which are orthonormal, right? And you can find the eigenvectors along that axis and the eigenvalues corresponding to those eigenvectors.
Actually, in order to even verify, we can take one of the vectors, take the dot product, the second one. It should be 0.
Yeah, we did that.
If they're orthogonal, it should be 0. You randomly pick any two vectors and take that dot product, np dot, and you should get pretty damn close to 0. Should be. That's what the theory said, right?
Right.
Yeah, that should be true.
Now there are 11 answers. 11 choose 2 possible dot products possible.
Yeah, all should be 0. 11 zeros. Yeah, we can't. I guess we can.
Maybe Maria, you can try that out. Tell us.
Why do you want to make me do that?
Just randomly, just picking one, and that will just give us good feeling.
Yeah.
Indeed, orthogonal.
That it was correct. That what we like. All that we did was what.
Some intuition. Okay, we're on the right path.
Will be very, very close to 0. I don't think it'll be exactly 0.
No, why is it not?
NP array instead of NP matrix. NP array you can give, right?
Okay.
Very, very. Oh. Minus 0.11299,247. Not exactly orthogonal. Okay. Maybe because of the approximation. E to the power minus.
I doubt
Because
that when we have such large data, we get accurate
in
values.
NumPy uses by default int. So if you really want to use it, you can do float 64 and then do that. I mean, or
Yeah,
float
for each
64.
one. I can't do that now.
Yeah, it's covered under numerical competition, right? So
Yeah.
Okay, what else? We had all the questions answered.
Yeah.
Almost. Want to hit 1 AM now.
Yeah. Right.
Which K values to take? I guess we answered that too, right?
Yeah. The ones with the highest.
Even I mean, this part, I guess that day when like we played around with the metrics and the image, I mean, that's what I remembered when I saw this. Like that day we we
Compared
played
to
around with.
the grayscale image, that's what you're talking about, right?
Yeah.
So if you think about now, I'll give a practical example, real life example. Let's say you're a shopkeeper. You have 11 products, right?
Yeah.
And each customer is coming in and each transaction is a row. So it's a linear combination of all the products because you're buying 2 soaps, 1 liter of this, that, right? And you're making some revenue. So now you have this transaction data stored as an n cross a matrix. N is the number of transaction, M is products, right?
Which
now,
products you keep?
right? Yeah,
Right.
without losing revenue, much
Right.
revenue.
Right. Nice practical examples.
Yeah.
So, which products to keep without losing
Minimum, what is the minimum number of products I must keep?
optimal solution for this,
Of
right?
course, you lose revenue because, of course,
Yeah.
there will be some customer who's buying product 11, but there are only total 4 of them sold in last 1 month, which translated to 40 rupees because it's 10 rupees off, right? That's
The advantage is to lose to keep minimum products, maybe like storage or something, and
Also, it
then
will
because imagine you are in a very expensive neighborhood. You are in a central downtown district where each square feet costs you 1,000 rupees.
right.
Okay. If space is a constraint, right, which in our case competition, right? So then you will be very judicious as to which SKU to keep. Then natural answer would be okay, fine. I'll only keep 5, top 5, right? That is our key.
Also, it will help you minimize the logistic cost as well.
Right.
So,
So I'm just
gets to that.
yeah. So image, I think sir discussed the image, all that, which is typically taught in most of the dimension reduction, SBD and all that. I just wanted to bring one more dimension, which is probably closer to data science that we see in real life and experience, right? So
Right. We probably won't be compressing images in data science. Yeah.
no, you will actually. There are a lot of places where you compress images, but it's just both textual data as well as but e-commerce data, whatever, these are all a lot more prevalent, right? So data compression is going to be there, whether it is image or numbers. I think Codasai 1, we did not have those. It took a little bit of time to understand. Not that we understand everything, but just slowly it's taking time to what I call settle down. Because as you take more courses, your knowledge is also becoming a linear combination of all courses, right? So finally, the lambda 1 and the V1 are emerging.
But also one more thing, I think this was something that Shivin and Rohit were mentioning one day, that they feel that this group is going faster than they when they were discussing this thing. I think much of this is actually thanks to you guys from previous coders, because you are the ones who are nudging us in the right direction, just asking the right questions, giving the right examples, so that we can get the right intuition for it. I mean, without the examples that we had today, I doubt that we probably would have understood this much.
Yeah, I think even I need to learn from Tebis. The way he brings up examples, I think it's from experience also that he brings it up. It is very nice.
It's just thinking, nothing experience, right? Nobody teaches you all this, right? So it's only after late stage in life you realize, but then it's useless. You don't get grades. It's like irony of life, right? So if you look at any financial services industry, I'm from that industry. I used to work. A classic conundrum, right? People who have a lot, banks want to give loan to people who have a lot of money. By the way, they don't need loans. And then there are people who need loans. Bank don't want to give loans to them because think they are not going to pay them back.
High
right?
risk. Right.
Yeah, same way, right? So the fine balance is, where there is a need and there is a demand and there is a supply. Similarly, here in data science and all that, there's tons and tons of data. We are drowning with data. So with big data, Hadoop and all that, we're basically throwing kitchen sink. We're storing everything. Now what happens in real life, there is this Pareto rule, right? 20% of things create 80% of the value. That's true. So why you want to keep all 100%, right? If I can be a little bit smart, instead of storing 100 gigabytes of data, I can actually make most meaningful analysis by storing 20 gigabytes. Now, 20 gigabytes can be probably loaded into some memory and will be done faster. 100 gig will take 5 to the Q, 125 times.
Right. That's why we keep
we're talking about 1 minute versus 2 hours. That's what we're talking about. So basically there is called cost of dimensionality, right? So So this is where big data is a big problem, right? So if we can figure out method to this madness, that we still understand that the real value always remains in a very small subset, right? If I take a big rectangle by matrix, which is 100 cross 100 matrix, but if I consider a northwest corner 20 by 20, that's where the cheese is. Rest is just all water, right? I'll only eat that cube 20 cross 20, which I can digest. But if I try to eat a slice which is 100 by 100, I'll run out of time, money, space, whatever, right? So that is what it is, right? So why we are spending so much of time and energy to compress data dimension is to make a complex problem simpler. Otherwise, we'll spend hours. It's talking about hours and days versus minutes, right? So business world and other people will not have patience to understand your 99.99% accurate answer. So this is where, as long as your reconstruction error is less than 5%, good enough, because most of the people in the business world make decision from gut. But if you can make it at least 95% accurate, you're making a huge improvement in your decision making. Ultimately, our goal in data science is to make decisions under conditions of uncertainty. If you can make it a little more certain, then I think more or less will go in the right direction. Like your gradient search, business will move in the right direction, make more profit. Otherwise, it'll close.
Also, in addition to that, I think computational power comes into play as well. The larger your data, the more computational power you need. So it's not feasible for you to deal with such large data. Not everybody has supercomputers at home. So I guess that makes sense, the dimensionality reduction part. In that
So you are loading data to pandas. Pandas loads everything to memory. Okay. What is your RAM in your computer? 16 GB, most of the laptops.
Right.
If you're using Jupyter Notebook and pandas, I give you a data set which is 25 gigabytes. No, not even 25 gigabytes. I need to give you only 100 megabytes of a CSV file. Can you do anything? Only 100 megabytes. In real life, you're talking about gigabytes and terabytes. Only 100 megabytes also we cannot analyze. Even with the modern laptops and computers, right? So this is where, while we are all becoming smart, at the same time we understand that there is limitation with our computing power. So let's make a big problem a small problem without sacrificing the complexity of the problem. And the answer we get is still very close to the most ideal optimal answer. By the way, that is exactly the MLF in one line, right? So it's essentially, there's a complex nonlinear curve where we are trying to find a linear approximation in the closed neighborhood. It will be very close. That f of x equal to f of a plus f double dash x minus a. That's all we're talking about, right? So if you can take a small linear approximation in the closed neighborhood, then we'll get a good answer. And this is the fundamental principle that machine learning uses to get very quicker to the answer. But if you talk to a mathematician or a statistician, they'll try to be a purist and they'll try to take very, very mathematically approach that x prime x inverse x prime y, which is regression, right? Which also will be covered in MLF. That is order n cube. So then you say, okay, why we need a gradient descent? So there's approximation. There's a theory, but then there's an approximation, right? How we can do it in a smart way using heuristic. That is where I think the dimension reduction and some of these linear approximation we studied in math 2 will come to our rescue. Yeah, Taylor series, somebody is mentioning. Yes, Taylor series only with the first one term, right? 2 terms. That's it. Yeah. All right, I think we are done. Anything else, Chetan?
No, sir, I don't think we have anything else for today. I think we can wrap up if you guys want, or we can start with the linear algebra 75.
Yeah, Devasmith, I wanted to ask, have you completed the 75 questions? I feel we have, right? Together?
75, no. We have done only 35. Then 40 were remaining. So I think hopefully we cover those 40, unless the 75 set has changed, it's still the same 75.
Same.
75, sir.
Yeah, I remember one number 8 or number 12 took 8 hours. So,
okay.
there are some nasty ones there, right? So it will take you hours.
Right.
1 day, 1.5
Believe
days.
me, these people go through it very smoothly. I feel, yeah, I don't know how. I think it's maybe because of the guidance. Like I try not to impose the idea, but maybe guide them in the right way. But we kind of are able to complete quite. I think we finished around 22 questions yesterday, just yesterday. But obviously, that's obviously the fruit of what we've done for the past 1 month. It's been a month since we started discussing linear algebra. Yeah, so I think we'll be able to complete it pretty soon. And I've
That's
completed the 75 questions at least 2, 3 times. I've taught I taught Pranav first, and then I taught Ananya and Nitin. So I'm kind of I really like the flow of those questions. I feel everyone should definitely get a chance to go through all of them. I think even Bharat here has gone through the entire 75 questions.
Yeah, that's really great. So I think then it will move even much faster in the subsequent generations.
Yeah.
Yeah, sure. And we are also, so we are trying to make it easier for the newer ones. So we are trying to create resources for the same, for the modules, for the linear algebra 75, for the topics we are discussing. We are trying to come up with these notes, crisp to the point, trying to come up with these videos that we are planning to record. Winner did pretty good job, pretty banging job at one video that we recorded. So yeah, I think what you're saying is correct. For the next set of people who will be joining, it will be even faster, right?
Yeah, absolutely. It's amazing to see the progress.
Yeah, yeah. Vinay, can we start with the linear algebra 75 then?
Sure. I think that's what
I wasn't there yesterday, so
Yeah,
I only
same.
covered till the 15th one or something. Maybe you guys.
I didn't even
Yeah.
cover till then.
Yeah, he wasn't there.
I yeah. Oh yeah,
Only
you weren't there.
Nishan and Ankit.
Ankit,
Only
right?
3 or 4 of us. Not sure how many people were there yesterday.
Yeah, Ankit had holiday, right? For
Now he
November
was
4th.
looking very tired. I was like, please go sleep, man. You look. He was closing his eyes with this video on, and I was like, this guy looks so sleepy. Please sleep. I'm not going to keep you here any longer. Ankit, are
Yeah,
you
oh,
there?
even Bharat kind of fell asleep. Yeah.
People sleep and they come back. They don't go to sleep. They come back.
Like Maria yesterday.
Yeah.
Yesterday she was like, yeah, I slept off, but she joined at like 2 a.m. or something.
No, I was in the train yesterday, so like yeah, I had to sleep because like my train would reach by 6:30, so if I didn't sleep, like I wouldn't wake up
You
by
would
that
miss the
time.
station.
Yeah.
Yeah.
Okay. Then maybe we can open those notes that we made that day, and let's go through those quickly, and
Sure.
then continue from the where we left off.
Which one did I use? Nice question.
20th October is the second one. Linear algebra class.
Class, is it? Class
Yeah,
was
class.
when we did it for all of them together, right?
Oh,
Yeah, this is
I
very
don't
old.
remember this. I don't remember this.
It's quite old. Oh, this is the one we used for the 9 p.m. class ones. Remember we covered around 8 questions?
Right.
Yeah, this is that set of questions. I don't think we made notes completely for
No,
anything. I mean,
no,
this is
we
just,
haven't. We haven't.
yeah. So maybe I'll just open the questions first.
Yeah.
Matrix Mystics is here. Oh, sorry.
No, Ocean goes.
This one only. Yeah, my bad. So maybe just go through what we've written for the first few because I think it's just a repetition of what we've done many times. What does okay. What does the matrix remind you of?
Function, information, encoded information of where I cap and J cap is mapping.
Yeah.
What else can be there?
Specific eigenvectors to this matrix. a new view to the matrix.
Yeah, right.
No, I mean we can still say stretching of space. That is linear transformation and stretching
Correct.
along eigenvectors also we can say.
And a linear transformation, a linear combination of column vectors.
Yeah, linear combination of column vectors. Yeah, so it can represent set of linear equations,
Correct.
helps us to solve them as well.
Mhm.
Then what is a function? A function is a black box that takes input and gives us an output.
Something that we give input to and it returns us the output. Correct.
Yeah, and the main things we need to understand is domain, codomain, and range. Domain is a possible set of inputs.
Yeah. Right.
Codomain, possible set of outputs, and actual set of outputs.
Right.
I think this is very clear. Range and codomain are different. We realize that. Pre-image. Yeah,
We've discussed surjective, injective. We've discussed this.
Yeah, surjective is onto, and range is equal to codomain. It is onto. If it, yeah, for no two inputs, if it has this, I mean, for two inputs, if they have the same output, it's not one to one. So
Right.
1 to 1 is when they have unique input output mapping. Yeah. This is not guaranteed. It is possible that a function can be 1 1, but not onto as well. Right? We saw examples of that. Question. Oh, I have a really nice question actually. Since we know what linear transformations are, if a linear transformation is 1 1, does it guarantee onto? It's a very nice question to think about.
What do you mean linear transformation is 1 1?
If a matrix is 1 1,
Mhm.
does it guarantee that it is onto? Let's stick to square matrices, maybe not generalize it to rectangular matrices. That we can think about later. Obviously, rectangular matrices will never be onto, right? Because it's, I mean, could it never be onto if it is mapping higher dimension to lower dimension?
Okay, if you want both, if you want both onto and 1 1, you need a square matrix. You cannot
Good
have
observation.
otherwise.
So when
Let's
you are
think about
talking
yeah.
linear transformation, are you going to a high projecting or going to a higher dimension, same or a lower dimension, right?
Yeah, let's do step by step, right? Let's do square first. Same dimension first.
Same. Rn to Rn, whatever.
Yeah, R to Rn, right? So yeah. So if I have an Rn to Rn, if the function is 1 1, does it guarantee onto? Is the question.
Yeah, in the case of Rn to Rn, I think if it is 1 to 1, it will also guarantee that it's going to be onto. But if we change the domain and codomain, say they are not say Rn to Rn, we have some Rm to Rn, and say Rm is greater than Rn, then
No,
I
first
think
question,
it
why?
will.
Why do you say that it has to be onto? A reasoning? I think mathematically we saw it actually.
Did we do
Not mathematically, maybe. How
Did
do I
we?
say this? I mean, there is a simple intuition behind it. Maybe that we can say. Maria, I remember we discussed this. Not sure if you remember. If a linear transformation is 1 1, does it guarantee that it is onto, given that it's an Rn to Rn?
Vectors.
Don't remember. It's been said.
Yeah, I don't.
We use the idea of just vectors. We use the idea of vectors, like it's just providing and AX, and it's just some sort of linear combination of columns of A. So if we can get for a particular output, is it feasible for us to get multiple inputs? So if we see that columns of A are independent, then the answer is no. So then definitely it's both 1 to 1 and 1.
Yeah, I think you came from the root of, since it is invertible, then it has to be onto as well, right? But can you use the property that since it's 1 to 1, that it is onto? I mean, okay, maybe a easier way to think about is, so okay, say it is 1-to-1, right?
Mm.
So every point in Rn is being mapped to one point in Rn.
Right.
Then you can think about it, right? Since Rn, every point is just being mapped to one point, all points in Rn should have a unique point in Rn as well. Right? So now you realize that the entire Rn is onto, like the entire Rn has a pre-image. Every point on Rn has a pre-image, and it is
The
unique.
moment you say that it's we are getting a unique output in Rn from Rn, you are taking all possible points from Rn and you are getting unique outputs for that in Rn, right?
Yes.
Essentially, what you will end up doing is you will have output in Rn for every input in the domain. So you'll end up proving the point that it's where if it's 1-to-1, then it's on to as well, as long as you're going from Rn to Rn.
Yeah.
But if you change the dimensions for it, say your codomain is smaller than the dimension of your codomain is smaller than your domain. In that case, if it is 1-to-1, okay, first of all, it cannot be 1-to-1. In that case, it can only be on to. If your codomain is small, the dimension of your codomain is smaller than the dimension of your domain, then it can only be on to. It can never be 1-to-1. And if it's vice versa, if the dimension of your codomain is larger than the dimension of your domain, then it can be 1-to-1, but can never be on to, because since you're having only 1-to-1 mapping, you can never cover all the um, values in your codomain without having one to many mapping. In which case you will have ambiguity in your output, and hence maybe
Yeah. It's good that you understood it. See, that's what the logical understanding is more important than the just reading it that okay, it cannot be 1-to-1 onto, right? Yeah, perfect. Right, Maria, you wanted to say something?
Hello.
Yeah, but you understood this point, right? Like that Chetan
Yeah,
mentioned.
yeah.
If m is less than n, if say R3 is being mapped to R2, it can never be 1-1 because you have points in R3, which is R3 is a bigger set of points than R2, right? So think about the sizes of the points inside these sets. That's what I would think about.
Yeah, right.
R3 has more points than R2, right? So if R3 has to be mapped to R2, there's not enough points in R2 to be able to have a 1-to-1 mapping. So
Right.
it can never be 1-to-1, right?
But can be on to.
Yeah, it can take the entire
R2.
It can cover the entire R2. That's what he means by onto,
Yeah,
right?
right.
Okay.
So if you have more number of inputs than more number of possible outputs, then what you can have is you can possibly map to all the possible outputs. But what you cannot have is have a unique output for each input in your domain, because your set of inputs in the domain is larger compared to the set of possible outputs in your codomain. So
And it cannot be onto as well, is it?
no, it can be onto. It can be onto. If you have, say, let's say, let's dumb it down. Forget about matrices, forget about dimensions. Say you have 10 elements in your domain. Okay, 10 elements in your domain and 5 elements in your codomain. And if they are 1-to-1, say they are 1-to-1, then you can possibly map all the 5 elements in your codomain to some pre-image in your domain, right? But what you cannot have is all possible inputs from the domain mapping to
A unique.
to a unique output in the codomain. That you cannot have, right? So, and if it's vice versa, say you have 5 elements in your domain and 10 elements in your codomain, and you know that you have one-to-one function, that is each element is mapping uniquely to the
It can't be
it
onto.
cannot
Okay.
be onto,
Yeah,
because
yeah, I
you
got the idea.
don't
Yeah.
have enough inputs in your domain. You can only check for onto and one-to-one when your domain and codomain have the same dimensions. Only then you can check. And even in that case, once you prove it that it's one-to-one, you don't need to check for onto, because it's going to be onto,
Yeah.
since the dimensions are the same.
Very nice. Yeah, I felt that was a nice question to ask at that point as well. Very nice. Bijective we are all aware about. If it is both 1, 1 and onto, right? Did we get a new view of bijective like recently when we were talking about?
Yeah, row space and column space, right? We
Mhm.
found out that there was bijection between row
I
space and column.
wasn't there. Yeah.
Okay, so just maybe think about it. Okay, I'll share just a second. When I'll share the graph to that,
Sure.
just show that graph and we'll talk about it. Just give me a second. It was bijection and row space. Okay, let me share the link to this.
Bharat, this would not be the proof exactly. I don't know if this is it can be called a proof, but yeah, I think I will
No,
call
it
it
is not a proof.
intuitional.
Yeah, it gives you intuition, but it's not proof.
Proof is in the pudding. Jadalat. Pudding. Yeah. God, you're making me hungry. I already yesterday we were ending at 4 and I was already so hungry. I was telling these people. We
4
ended
a.m.
this. Yeah.
Yesterday, 4 a.m.
Yes, sir.
My
Yes.
God. Wow.
I left early. I had some sessions to attend to in the morning. I left early and I asked Vinay the next evening, okay, when did you guys sleep? He said 4. I stopped right there. I didn't ask him any more questions afterwards. Yeah, this is the graph. Yeah. So if you look at, okay, it has a lot of things. I'll just okay, yeah, stop it. Yeah. Can you look at the row space and column space of the matrix, Maria? I have plotted those. This 1, 3, and 2, 6 is the matrix, and I have plotted the row space and column space for that.
Row space is green and
Yeah.
column space.
Column space is the purple color, and on the lilac I have plotted the null space for that. And that angle between the row space and null space shows that it's orthogonal to each other. They're orthogonal to each other. And on the null space and the row space intersection, that is the origin, you look, there is a cross there. Okay, that cross is the resultant of when I multiply a vector on the null space to the matrix. And what we observe here is, no matter what input we take from the null space, it's giving me one unique output, that is the origin, right? That's what we already know. That's what null space is, right? That's what null space means. All the possible set of vectors that take you to origin when inputted to a matrix, right? We only talk about null space in terms of matrices. Otherwise, null space doesn't make sense. You don't talk about null space in terms of a vector. There is you only talk about perpendicular vectors to that, but you don't talk about null space when you're talking about vectors. You only talk about null spaces when you have a matrix. So it is a set of vectors that give you that take you to the origin when inputted to a matrix, right? Okay, let Vinay stretch for a second and then we'll continue. Oh, it becomes very tiring. Okay, it becomes very tiring. I am glad he's doing it. I should do it more often.
Yeah, I'm also thinking of going down and filling my water bottle. I finished it.
Yeah, please do, please do.
Mm.
So
Awesome.
I can share it. I can share the screen. I have the graph with me. You go and fill your bottle till then.
Thanks.
So you just take a look at it. That no matter what input I'm giving it from the this null space, the output remains the same. The output is J, right? That's what we are looking at here. Now, if I stop it, and I'm just going to show you some things. Okay, you just need to observe those. So now I'll do one more thing. What I'll do is I'll plot another line, that is this. Can you see this another line?
I
Right?
mean, I remember, yeah, I
Okay,
think I was there till you guys discussed the part where, like, when you use lines parallel to the null space, you
yeah,
get
I'm
different
coming to that.
points
I'm
along
coming
the
to I'm
column.
coming to that. So you just see that it's parallel to the null space, right? I'm taking a point O on this, and my P is the output for that. Let me increase the size for it so that you can easily view it. And you see this point O, right? The point O is a point on this perpendicular line, perpendicular to the null space. I vary this point O and see what happens with P. It doesn't even change. It doesn't even budge. My O is moving. My O is changing its value, but my P remains the same. It's 300 comma 600, right? Now now let's plot another line to see if it's the same for that as well. Okay. Do I have, yeah. So this is another line, minus 1 by 3x plus 200. I am taking another point G on this, and I'm plotting the output for this. This is the output for this, H, right? If I'm reading the inputs from this line, what I'm seeing is I'm getting one single output, right? One single output. And one thing that you observe here is, for every line that I plotted, that was this line, the output was on the column space, which makes sense. When we take the column picture, we are actually taking the linear combination of the columns, right? Our resultant is the linear combination of the columns, so it will lie on the column space, right? That makes sense. So now what we did here, we observed this part, that okay, yeah, when we take parallel lines, it gives us point that are unique, and for every input from that line, it doesn't change, it remains the same. What we did next was we took line that wasn't parallel to that. We took a line that was at some angle to that. We took a point K on that, and we saw what the output is. So the output was this L. Okay. If you take a look at it, now if I vary the K, you observe that L is varying along with it, right? But still lying on the column space, which again makes sense because it's nothing but the linear combination of the column vectors. So hence it will lie on the column space. You see that this is varying, and and hence L is varying as well. We again verified it by taking another example, that whether it's happening for all or just this case. So we plotted this another line. We varied, this N is my output and my M is the point on this line. So when I vary M, my N also varies, right? My N also varies. Now, these were the observations that we made through the graph. Then we tried to make sense of out of it. We observed that any point that I can take on this R2 that does not lie on this null space can be broken down into its components, right? Any point, any vector that I can take from anywhere in this R2 that does not lie on this null space can be broken down into its components. And okay, maybe is Vinay here, or Ankit? Do you have your iPad connected? Okay, Ankit is not. Ankit, do you have your iPad connected?
Yeah, but just give me
Yeah, yeah.
2 minutes. Let
Okay,
me.
okay, you go ahead. Okay, no. You go ahead. Have a good night. You, yeah,
Actually, I have a few
I,
questions
No, we'll wait for Vinay. We'll wait for Vinay. It's just a small thing. You go ahead. You have some good night's sleep.
No, actually, I have a few reflections on what I taught.
Okay.
So
Okay. Perfect. Yeah. Then go ahead. Till then, I'll just try to verbally explain to Maria. So every vectors that you can take on the entire R2 plane, Maria, you can essentially break that down into two components. One is a component that lies on the null space, and another one component that is perpendicular to the null space. Right? Those are the two possible components that you can break it down in. The one component that actually lies on the null space gives you 0. It gives you 0,
Yeah.
right?
Mm-mm.
But the component that lies perpendicular to the null space will give you a unique output on the column space. Correct?
Yeah.
And this was the major breakthrough for understanding this whole thing. After that, we realized that any point that we can take on R2, any point we take on R2, we can think of it as lying on some line that is perpendicular to the null space. That was another explanation that we got. That any point on R2 can be thought of as lying on some parallel line that is parallel to the null space. Right? So we saw that every point on a particular line maps to a particular output on the column space. So we observed that any point you take on the row space, since row space is not not parallel to the null space, it is at some angle, it will intersect the null space at some angle. So what you can do is every input you take from the row space can be broken down into two components. That was Ankit's way of explaining it, and Vinay's way of explaining was that you can think of it as lying on some parallel line parallel to the null space. Okay, both makes explain the same thing. Essentially, what you can think of it is every point on row space will give you a unique output on the column space, and hence we observe that there was a bijection from the row space to the column space, even if your matrix is not composed of the independent vectors. We don't care about that. Even if it is not composed of the independent vectors, if even if there are even if it is not a full rank matrix, we observe this bijection even in those cases. So this was the whole bijection between row space and column space, and Ankit will show you the explanation.
Pub, just a few points to note here, like that I means we avoided in the discussion. Actually, if you see these lines, or just let's just build up the basis first. This complete space can be seen as just collection of points. Yeah.
Yeah. And every point can be thought of as a vector. So hence we have a R2 plane is nothing but a full set of vectors, but we don't represent it as vector because it's tedious. It's easier to think of it as a plane, right?
Yeah. So essentially, we can see it in different way, like stacking of different planes, like this thing, this thing, this thing, and so on. So we can see the just stacked version of different planes, one top of another. So essentially, we can define the complete space using two directions itself. One is like here in the coordinate system, we were using I and J cap. So to define R2, we just need two directions, nothing more. So what happens if we are considering this our direction when we are considering our direction along this and another direction that is just perpendicular to it, we can still define our complete space. First
Yeah.
verses. Yeah. Now another point. If this thing is your null space, then whatever you are having for a times x, if x is your null space, it will lead you to the origin.
Mm-hmm.
And for any another line that is not that is not null space, but is parallel to null space.
Yeah, you'd get points. Yeah.
Yeah. So this line again can be thought of just collection of points, first thing. And in that collection of points, we can definitely see it as effectively these vectors, various vectors that are from origin to this line.
Mm.
So if we take instead of ax, if we provide x to be any vector that is pointing to this line, then this line would essentially have two components. One is this, let's say is G2, and another say it's G1.
Yeah,
Nothing,
okay,
just
yeah.
write
So
down the
one is perpendicular and one is parallel. Okay, yeah.
yeah. So X becomes our G1 plus alpha G2. Why I'm writing alpha G2?
Oh,
Because
that's true.
it's not just AX that is being mapped to 0. It is the complete null space that is mapped to 0.
Yeah, the whole line is being mapped to zero. Okay.
But
So
the
G2 is like the units vector in that direction. So yeah, okay, yeah, got it.
but G1 is something specific for a line.
Mm-hmm.
So if I provide it as an input in place of this X, then what does it brings? My result will be essentially dependent upon G1 because I know it is simply this A times
Yeah,
alpha.
alpha G2 will be the origin. Yeah.
It
Your
is just
alpha G2
zero.
is not contributing anything to the result.
Mm-hmm.
So whatever contributing to me is alpha G1, and that is just a particular input
Vector.
for a complete line, just a particular vector. Now here comes a different idea that we can see this any matrix as a combination of columns, and for a uh, particular x, we can see it as x1 times c1 plus x2 times c2 plus x3 times c3 and so on. Just the linear combination. Now, if we provide, it's here. Do you agree, Maria?
This
Yeah,
is
yeah,
nothing but
yeah,
the
this is fine.
column picture, right?
Yeah.
So if in a different system, what I say to you is, you are having one vector this, another vector this, and you are taking the resultant. So this is resultant. This is V1. This is V2. So yeah, if these column vectors are independent, even no, just see, first, just tell me, like, can you get this R through any another combination of V1 and V2? First thing.
Any other combination of okay, like
Can you get any another this R using any another combination of V1 and V2? Is it feasible? No, na?
I mean, if V2 is along the x-axis and you have like okay, yeah,
But the
your
magnitude will
V1
still
has
remain
to
the same.
originate from the origin, right? Yeah, then no.
Actually, V2 is also originating. I just have shifted.
Yeah.
Same
Yeah,
thing.
yeah, yeah,
It's
yeah.
essentially
Then no. Yeah, then no.
it's I have drawn this V here, V2 here, but it's essentially is like this thing.
Yeah, yeah. Yeah, that was the other possibility that I was thinking of. Yeah, so no.
Yeah. So if our G1 is not having any component, means we know that one thing more. G1 is perpendicular to this thing, null space.
Yeah, yeah.
Why? Because G1,
G1 is the distance from the null space to the line parallel to it, right?
yeah. And what G1 is represent is row space.
Yeah,
Because
yeah.
row space that is perpendicular to.
Perpendicular to null space, yeah.
So if we are having A times G1, that should be mapped to a particular output which is unique,
Mhm.
because you cannot expect a resultant using any other combination of existing column vectors in the system.
Mm.
So if I take this was your G1 thing, essentially your row space thing. And this is your column space. Column space is also the output space of a matrix. Yeah. Means wherever you all the outputs of a matrix will lie
Yeah, will on the
the.
column space, yeah.
So if I'm saying that I'm providing a G1 and it is providing me something unique, then that unique will be inside column space only.
Yeah,
So what does it ensures that if I am only along row space, then I have a particular point only along.
column space, yeah.
That's one-to-one mapping and on-to mapping both.
No, no,
That
no, no, no. That's one-to-one mapping, but similar to what we discussed in linear transformation, it ensures on-to mapping because your column space, the dimension of your column space and the dimension of your row space is actually same. So when you have one-to-one mapping, it ensures that it's onto as well, and
yeah,
hence it's bijective.
yeah, but that thing I didn't say because of this thing, because of this logic,
Because of what?
because of this we just saw that because you cannot expect to get R through any another linear combination of V1
Yeah,
and V2.
that's what on one-to-one means, right? That you for any unique input from the row space, you're getting a unique output from on the column space. But that does not guarantee it's on to if the dimensions are different. Only because the dimensions of both are same, it satisfies the property that it's surjective, that's onto, and
But
it's bijective. Also, one
remember,
more thing that we cannot have the different dimensions for row space and column space. The rank will be the same for both.
yeah,
It's
the
also,
rank is always same for the row and the column
but the
space.
correct way would be the same approach that we took for the linear transformation. That would be the, I think, the correct way to say it.
Yeah. In this here, we now have some bijection between row space and column space.
No, wait. I want to understand one thing. I want to understand why row space is equal to column space using this. I don't want to use
No, I'm not saying row space. I'm saying rank.
Using what?
Let me rephrase it. I am saying that it's the same thing that Chetan said, that the rank of row space and rank of column space is equal. That was that I wrote, not the wrong.
that's
They are
understood.
different. Yeah.
No. I want to understand that concept using this. That is what we're doing here, right? What I feel is we are literally looking at the rank nullity theorem in one sense. I don't know if Devasmith is with us. If he's there, he can also let me know if what I'm
There's
thinking
something
is
that I
right.
realized as well today, that you remember when we were taking a vector in the R3, what we were getting is the perpendicular object to that. You remember, guys? We were getting a plane, right? An
Yeah,
entire
that's
plane
what,
full of vectors, right?
that's what we discussed, right? That pencil and the
Yeah, the
column
umbrella.
vector was the pencil and the pen was
Correct.
the paper was the null space.
Right. The inverted umbrella, right? But today I was thinking about it and I observed that what is the dimension of that one vector? What is the dimension of that?
Vector meaning the null space vector.
Not the null space vector. The next vector I took in the R3. What is the dimension of the line that passes through that? One, right?
Yeah.
The line. It's a line. One. And what is the dimension of the object that is perpendicular to that? 2. It's a plane. And what do you get when you add both of those?
You're understanding. So he's trying to understand the rank nullity theorem through the fact that since row space and null space is orthogonal,
right,
and orthogonality always together create the entire space.
Correct.
Right? When we took a vector in R3, we saw an entire plane was perpendicular to it. And if we take the same vector in R4, there will be a R3 plane that is perpendicular to it. And since row space is perpendicular to column space, sorry, null space is sorry.
Null space.
I'm so sorry. Yeah. Null space is
perpendicular to the row space.
Yeah. Row space. Yeah, then he kind of realized that it has to be the case.
It
Which
gives
is
me
very
the
nice.
entire R3. It gives me the entire R3. I was thinking about it and that I realized, okay, this is happening. And then I thought, okay, maybe it was just a fluke. And I thought, okay, let's check in R2. What do we get in R2? And we get the same thing in R2. We get a line, and we get a line perpendicular to that as a null space, right? Essentially, what we get afterwards is we have two orthogonal set of vectors, and which will essentially give you the entire R2, the linear combination.
Yeah, because in the example last time we were using only R1 versus R1 because our null space was one and column space one. That's why I said, okay, I mean, it just happens to be a special case. Orthogonality doesn't mean that both the spaces should have similar dimension, right? So this is where here it is 1, 2. It's generally, M and N, and then total is M plus N, whatever, right? So
And I think now we can, it becomes, since we've understood this, it becomes easier for us to answer a question that, okay, say I have a higher dimension Rn, and I have an object in there which has some m dimensions. What would be the dimension of my null space? I can easily answer that now. It becomes,
Well, I mean, yeah, the best way to think was that if you take a dot point, right, which doesn't have any dimension, I try to represent that dot in R1. What will be the coordinate system I'll need to describe that dot? 3, right? Let's say it is at marker 3, my scale. Now suddenly I say, no, I'm not going to display it on R1. Same object. Now I try to represent it on a piece of paper. Then I certainly take my geometry and call it X and Y. So the same object is now, based on my origin, I decide it is 3, 0.
right.
Now I said, no, it's in a room. The same object is actually not in my paper.
In the paper.
It's in the room.
Right.
So again, I describe it as 3, 0, 0. Now
It's
you
a
realize
three-dimensional thing
the
now.
dimension hasn't changed. All I'm doing is to describe that object. I can do very well just using R1, but I'm wasting energy by describing it in a paper or a room. So similarly, data, the tuple example we talked about,
Right.
To describe its true nature, we don't need a tuple of 11 dimensions. We are okay with 5.
Right, correct. This is actually one of the small things that we discussed a couple of days back. I think me and Vinay were talking about it. That if we have a point that is in, say, a higher dimension with all the other values being 0, should we call it a object of that higher dimension, or is it essentially an object in lower dimension? And that's
Yeah, so it is like two things. What is the true dimension of the object and where you represent, or the point in which you are looking at, right? So if you're talking about a customer's data, if you take only age and height, then you're describing that object called customer using only 2 dimension.
Right.
Certainly age, height, and how much they have transacted, so you add features or x1, x2, x3. Then essentially the tuple's dimension is increasing to describe that object of interest.
Right.
So that doesn't change the object in itself. You're just trying. Now, if you over describe, you're not really, adding a lot of value, because like you have taken age in height and age in inches. Sorry, what are we talking about? Height in inches and height in centimeters, right? You're really not adding any value. It's really
redundant statements. Both.
redundancy, right?
Yeah.
So increasing dimensions artificially without really adding any value.
Yeah, right.
Description of that object. So it's kind of commonsensical way of trivializing this concept of the true object is actually belongs to a lower dimension.
Right.
Intentionally chosen a higher dimension to describe it, but
Effectively hiding in a higher dimension.
So understanding linear algebra will make us understand that we can actually describe it very nicely in RD. Why we need Rn, which is much larger. So it will come naturally through the data. And when we understand the natural, what the data is telling the story, will determine what is the appropriate D for the matrix. Then rest becomes n minus d, or k. So n minus k becomes superfluous. It doesn't add a lot of value. It's in case of orthogonal, it will be 0. In real life, it's not orthogonal, so you'll get 0.0000001, right? That's all. So that is why your reconstruction error will be almost negligible.
True.
This Chetan, the thing that you said, like it was pen and paper.
Yeah.
One thing is definitely certain. If your null space is a plane, then your rank space here row space was a line when you are considering this umbrella thing, na? But collectively, you know that row space or column space rank is your matrix rank. Even if null space plus row space completes that dimensional thing, like null space was a two-dimensional plane, perpendicular to that was the row space. essentially they can form R3. Yeah, I agree. But this thing certainly does not have to do with the matrix itself,
Oh, no,
essentially.
I never said that. I never said that it's equal to the rank of the matrix. I think that's what Vinay pointed out in the chat as well. I
Yeah,
said it gives you the dimension of the vector space it lies in.
yeah,
Exactly.
vector space we can say.
Yeah, that's why Vinay put it there. I thought you'll figure it out and rectify it, but I never said that it's actually equal to the rank of the matrix. You can't get
My
you.
bad. I didn't pick that. So discussion was going, so I thought that I will get
No
it.
issues, no issues. So
Yeah,
it
so rank is nothing but row rank. I mean, rank is equal to row rank is equal to column rank. That's
yeah, and rank is just a fancy way of saying the dimension. Okay, it's the dimension. It's the dimension of your row space. It's the
yeah,
dimension. It's the dimension of what is nullity. It's the dimension of your null space.
yeah.
What is rank? It's the same thing. Okay, so essentially what they give you is the dimension of your vector space, the whole thing. That's
Now continuing with this topic itself, what we wanted to understand is, will we get unique? What is the nature of B itself? Will it this for a particular input to AX, will our B be unique or different?
okay. See, for this, I think this gets into that whole thing. Is your matrix A invertible or not?
No, I don't think he's
Uh,
talking.
let's build upon the same thing that we did now. No? It is just alpha G2. X we can write it. Yes, it's into component form.
Yeah,
We know that AG1 gives us something unique.
right.
Plus, this does not gives us anything, but it is part of X. It is still part of X because X was our this thing G1 plus alpha G2. This you can see here, this thing.
Yeah, right.
You know?
Yeah, we remember it.
Yeah.
Okay.
So for any for the same G1, if we are having multiple G2s, our output is essentially same.
Yeah.
So,
You're trying to prove the same thing, yeah.
yeah. So multiple X are mapped to unique. If this X was on this row space, only then this alpha G2 component was 0. But if we see it from the perspective of input and output, we always have, if we want to map reversely from B to X, we can still map it to multiple inputs. One thing.
Right.
On this same perspective that we further connected on was this thing.
See, the only apprehension I have with this is, um, so the matrix multiplication part actually works a bit differently in some scenarios than algebraic calculations. So I don't know if it would be the best way to say this. See, I know one thing. If your matrix is a full rank matrix, that is all the vectors in it are independent, then the solution that you have, your X, would be unique for a particular B. It would be unique for a particular V. You cannot have any other V for that.
Yeah, but if we are restricting ourselves to inputs and output that are only in the row space and the column space,
Hmm.
then the situation changes.
In that case, you have unique inputs for that.
Yeah,
For any unique inputs, you have unique outputs.
yeah. Only if we are restricting our space to that.
Yeah, right. That's why we said, right, that even if we have a matrix that's not full rank, this idea still stands because see, this is very basic thing that we discuss when we study functions in maths 1. That you cannot say a function is a surjective function. You cannot say a function is a injective function without actually first talking about its domain and codomain. You first need to define, okay, in what reference are you talking about, whether it's this function is a one-to-one or on-to function. Once you have defined that, then you can talk about that. So what we did there was we restricted our focus to only row space and column space. That's why we only talked about bijection between row space and column space. We didn't even consider the whole matrix. We just said, okay, forget about the matrix. We don't care. You take dependent columns, you take independent columns, we don't care. This idea will still remain because we have restricted ourselves to only row space and column space.
Yeah.
That's why we were seeing bijection there.
Now, continuing on this, we certainly don't have solution for where our system of equation this solves for ax equals b because b is not in the column space.
Mm-mm.
Now, we further connected on this thing, if you remember earlier, that we drew a perpendicular and found this thing.
Right.
That's our best optimal solution.
Correct. The
Yeah.
biggest cafe problem.
But here comes one thing. The nature of x is not just unique to this thing. It is of some form this thing in alpha g2. It is something like your particular solution. And it is just your null space thing. So
I'm not getting
I
what you're
disagree.
trying to link here.
No, I disagree here. Are you saying that the x that you find, which is the closest to B, which is that perpendicular line drawn from B to that point, can you just point x on the column space for me?
Are you saying that wouldn't be unique?
No, he's not saying that. Let me
Okay.
try to.
Let me reframe it. Like,
Okay.
No, I want to understand your clarification, because if you are trying to explain something and I know you're wrong, maybe let me let me confirm it with you first, and then maybe we can talk about others. Okay.
this pink line is a line that is parallel to the null space.
Yes.
And any point on this line maps to B.
And where
That
is your row space? Where is your row space?
row space I haven't drawn for
It should
now.
be perpendicular to this pink line, right? Which
Oh,
you
no.
drawn just now.
Oh, okay. Yeah.
Yeah, it should be perpendicular to pink line.
Okay.
Essentially, I was not required row space here. Essentially, null space because I just wanted to see that inputs and output only. So row space does not play role there.
Yeah.
And because this completely x line maps to a particular b, a particular this thing, let's say it's b dash, that I thought was optimal solution. In such case where null space exists beyond origin, then we can have multiple optimal solution, not just unique.
Oh, no, mate. What you will have is a unique solution for that. That point that you have projected on the column space has a unique solution.
Sorry,
Your
output is unique, not inputs. Sorry, yeah, just consider this thing.
output is unique and the input is unique as well.
No. Consider this thing like you wanted to solve for ax equals to b, but you
Right.
cannot go solve for b. So you find a point b dash which is in your column space
Correct.
that best suits
True.
this
Yeah,
a.
you do that.
This has infinitely many solutions. You're right.
Why infinitely many solutions?
Yeah, think about it. Think about it.
No,
Maybe Chetan can think about it.
see, you have a point on the column space,
Mhm.
right? That
Yeah.
point is unique. That is the perpendicular projection of whatever your say your point B was. Correct?
But how?
Yeah,
Okay,
but
think about
it's
this.
a
But yeah.
combination of the
Yeah,
like
okay.
null. Can't your input be something plus the null space? So that would also give you B, right?
No.
Exactly.
See, your input can be that. Your input can be that. But that is true for every other case as well. In that case, you will never have a unique solution.
That's the thing. When your null space is the origin alone, is only when you get a unique solution.
Exactly.
That's why we write this as a solution, not just a particular.
Just a
By
second.
having
Just a
this
second.
and null
Just a
space.
second. Yeah, just a second. Let me think about it. Your null space is a unique.
Is the origin alone is when you get the unique
Right.
solution.
That's when we have the yeah, correct. You have all the vectors as independent in that case, right? Of your
Yeah.
matrix. All the
Yeah,
vectors
yeah,
of your matrix are independent. That's why your null space is actually a point.
yeah.
Okay. Yeah.
So no, I mean, do you see that ax is equal to b dash has infinitely many solutions?
Yeah.
Yeah, that's what I think you wanted to say.
Yeah, Ax equal to B dash has infinitely many solutions. Yeah.
If null space is beyond origin, then definitely it is.
Yeah. Makes sense.
Okay.
So
Yeah.
I mean, okay. I really wanted to see the bijection between row space and column space in
Yeah, I mean, like, okay, this is how much I understood. Maybe then, yeah, you can
then
add
like
on in between. Yeah, what I understood. So, yeah, so each line parallel to the null space would correspond to some like point on the column space. So obviously, yeah. So since um wait, yeah. Then what we did was
Can
yeah.
you
Can you
rephrase?
go up?
Can you rephrase the last statement that you said? Can you repeat that? Maybe not rephrase it, just repeat it.
Yeah, so if you have so the null space takes is the set of like that line would take all your
No.
would be the set of
Just
inputs
the
that take
last
it to
point that
zero.
just the last line you said. I just want to hear that. I uh, I think you misspoke something. I just want to hear what you said.
Okay. So if you have a line that's parallel to the null space,
Yeah.
that like the set of points on that line would correspond to one point on the column space.
Correct.
So if you take a large number of points on like large number of lines that are parallel to null space, like a lot of lines, you can essentially reach any point on the column space.
Not just the column space. You can reach for input. You can reach the entire R2. Okay, for entire R2, you will have some output, unique output on the column space for that. That's what we saw that.
Yeah. All lines, all possible lines parallel to the null space in R, I guess. Is that what you mean?
Yeah. With
Yeah,
that, you
okay.
can reach any point on R2. You can take any point as input. And for each input, uh, what you'll have is because it will lie on some line parallel to the null space. You can think of it in that
Yeah, and then what Ankit did is that, like, for each line that's parallel to the null space, we can actually correspond that to a point on the row space, right? So in that sense,
you can actually break it down into two components. One of those components will actually lie on the null space, and one will lie perpendicular to the null space. It's just the basic what we used to do in physics as well, right? You used to break down vectors into two components, right? Two perpendicular components, right? That's what we are doing here. One lies on the null space, and another one lies perpendicular to that. We are saying that the one that lies on the null space contributes nothing to the output, to the resultant. The only thing that's contributing to the resultant is the part of the vector that is perpendicular to the null space.
yeah, I got that.
And since it's fixed, the perpendicular part is fixed, you'll get a unique output on the column space. And also, the perpendicular part actually lies on the row space. Since row space is the subspace that's perpendicular to the null space.
Yeah. Is that it? I mean, what was the point of the last part that he drew actually?
Oh no. He was actually trying to uh, discuss the Baker's Cafe problem with this same new perspective that we found. And for a second, I didn't think about the fact that we are getting the null space to be a line instead of a point, and I thought that we'll get a unique output. So that was the discussion we were having. That, yeah, go ahead, Vinay.
Maria, I want to ask a question.
Yeah.
If I take, okay, let's say our null space is a line and we are in R2 and the null space is a line, and I take any other line that is passing through origin, which is not the null space.
Mm-mm.
So it is just some other line which is not the null space, any other line which is not the null space. Now I want to ask you, if I take points along this line, let's call the line one. Is it okay if Ankit, if you're there, you can maybe write it down, or maybe I can write it down if
No,
Okay.
just tell me.
yeah. So can you just maybe just go up actually?
Ankit, you
I
haven't
don't.
had your dinner, right?
I had, but
Like, if you're tired or something,
No,
it's
I don't
fine that,
blame you. I
yeah,
don't blame you.
even I have the writing pad, I can take over if, like,
no, actually, it's
tired.
bad. I was a bit sleepy a few minutes back, but now I'm back awake. So I
Yeah.
was
If you want, you can sleep since you have to get
Yeah,
up in the
oh my God.
morning
Oh yeah,
for,
right.
yeah, you do, right?
Yeah.
So it's
actually I was
fine.
having my transfer to my home district in a
Oh,
few
that
days.
would be great.
So I was busy today handling that matter. So I'm hoping that in further 2-3 days I will be posted near my home itself.
Nice.
Oh,
Now,
you got reposted. That's
yeah.
nice.
Now he has to
I I,
travel to.
I put a file and pulled some strings so that it will be easy
This
because
is
it
being
will not
recorded.
like
This is being
5 hours
recorded.
of traveling daily.
So we'll get to know about it. Don't worry.
Why are we still
You
recording?
travel 5 hours daily. Oh,
At least 5 hours daily,
Yeah.
at least.
daily in the sense one direction or both
Go
directions
direction.
together.
Go direction.
Both direction.
Yeah,
Direction is
yeah.
too much. What is this?
5 hours is a minimum time.
Yeah.
Oh God.
That's a lot of travel time.
His job is in, I think, Sonipat, right? Ankit?
It's currently it's Panipat. Sometimes I have to go Samalka.
Okay.
So
I
yeah,
haven't even heard of these places, so it's a bit
Oh, don't
funny.
worry.
Yeah.
Don't worry.
just
Oh,
consider this next district. I have to travel across district.
so Ankit, your house is in your row space. Obviously, the job is in the almost null space, I would say.
No,
Farthest,
that was
farthest
a
from
nice
the
answer.
farthest from the column. The outlier farthest from the null space, farthest from the column space.
Yeah.
Yeah. Anyway, Ankit, I think you should sleep now. I think Vinay can share this.
But yes,
With
but
No,
I will be listening
the
to you
joke
guys.
is doesn't matter. It doesn't matter what you do job. It will always give the zero output. So that's why it's a space.
His job is in null space. Oh my god. Okay.
Uh, But for me, I mean, everything has certain advantages. Like this job, I have wide connections all over the states, sometimes across the countries.
That's like spanning R2 for you.
Yeah, that is planning the complete. Wherever I go, I will find someone who I have met in some meetings or somewhere,
Right.
definitely.
I understand that.
Go ahead, Maria.
Yeah.
Yeah. Can you repeat your question? Sorry.
No,
Oh,
no.
he is asking you to share
Yeah.
the graphics tablet. Yes.
Oh, I thought, okay, fine. Oh, I have to connect it just
Have
a
a good
minute.
night, Ankit. Have a good
No, I
night.
have it connected. If you have to connect it, I
It's
can.
a good night, but I will be listening to you guys till I'm sleepy.
Lullaby. Oh my God. I just
Like, I'm
love
in
this
my bed
FOMO thing.
right.
I just love it.
Yeah. Did you guys put a thought on what I posted today?
Yeah, I
Yeah,
did,
actually, we
but
wanted to discuss that.
yeah, right.
Hmm.
I didn't fully understand
Right
it.
awake because I'm eating something chilled.
Yeah, I actually did think about it, but uh, yeah. So
Maybe doesn't know what we're talking about. Maybe we can post the same
Yeah,
question.
let me
Yeah.
Ankit made a few statements today on WhatsApp. We have a group there.
Group.
Yeah.
I checked that symmetric thing also. One that I said reflexive now. That thing I checked extensively and that failed. So I deleted that thing that I posted a few days back.
We have a group on WhatsApp for these insomniacs.
Oh, what's up?
Yeah.
One more, what do you call it? System in place where data will be hacked and
Right. So let me just post these statements.
Until then, I mean, you guys can look into it. Until then, I'll try to somehow draw a straight line. Awesome. I'm able to draw. Okay. So, yeah, say our null space is a line.
yeah, you wanted to take lines other than those which are parallel to the null space, right?
Yeah. Take any line. Any line. Can you give me a direction to start the line from? I'll go around the entire circle. You can tell me any line except the red line.
The
You can,
entire circle. Oh,
or you can tell me to stop anytime. I'm just playing a game. Anyways, tell me to stop whenever you want me to stop.
wait, I can't.
You
Stop.
can't see my okay.
Are you drawing another line?
Oh, can you not see the
Oh, I can
highlighters?
see the green
Oh, yeah,
dot.
we can do it.
Yeah, now I can see it. Yeah, okay.
I thought you could see it.
Yeah, we can see it.
You can see the green dot. This one, the one
I can
highlighted.
see the green. Yeah, I can see the green dot that's close to the red line. I mean, not that close.
Okay. So, okay, let's just say I'm taking this line, this weird line that is passing through this point and 0, 0, right? And let's say this pink line is my column space for some reason. This is my column space. So this is my column space. This is my null space. And this is a random vector, right? Random line. RL, reinforcement
Yeah.
learning. Yeah. So I want to ask you this question. If I take inputs along this line, right, from each point on this line, and I see the output on the corresponding column space,
Mhm.
what will happen? Like, will any 2 points on this line maybe have the same output? Maybe 3 of them will have the same output. All of them will have the same output, or maybe each one of them has a different output, what will happen?
Okay, so yeah, one component, okay, yeah, if I take a random point on that line, maybe I can, okay, you don't have, can we draw a line like which denotes the row space maybe? So,
Yeah,
no, is that doesn't help you?
row space is just this line.
Yeah,
That's
I hint here. Just consider what happening with the G1.
Maybe let Maria think. Let
yeah, let her try to build it up, because I mean, I don't want to see much math here. I just want to say, okay, I just want to see, I've taken these multiple points. I want to know if this, I mean, it maps to something. This maps to something. This maybe maps to the same thing
For
that this
the
first one mapped to.
for this part, you actually don't need the mathematical view for this. We have enough intuition to build on to get the answer.
Yeah,
Yeah, so yeah, uh you can decompose this line along the row space and the null space, right? So
maybe it's even simpler than that. Maybe it's even simpler than that.
Wait, what did you mean by decompose? I didn't understand.
yeah, you can, I
She's
mean,
approaching the same way the Ankit did, decomposing a vector into two components, one along the null space, one perpendicular to that.
yeah, I mean, since the row space component, like he already showed me how each point on the row space would correspond to a particular output in the column space. Like, since our components are also unique, we can also think of like you would get different points on the column space.
Do
Like,
you,
you
do you
wouldn't get
remember
a
that,
repetition either.
Maria? Do you remember what happened when we took a line that was parallel to the null space? What happened to the output? Do you remember that?
All the points on the line had the same output.
Right. Just build on that. That's the answer.
Yeah, I would say forget about this. Forget about this for a while. Just think about, I'm just taking a random line and I'm asking you what will the outputs look like? Like, will they have maybe the same output? All of them map to the same thing? Or maybe this one maps here, this one maps here, this one maps here, this one maps here, this one maps here. This one is mapping to the same one. I mean, I just want to know where the mappings will be for these points.
Just think about what we discussed there and just try to build on that. That's more than enough. You don't need anything else.
Okay, we'll start with one point on this blue line. What point do you know definitely the answer for?
Origin.
So this point, right?
Yeah.
So you know this point 0, 0 maps to 0, 0 in the column space, right? Okay, you started from here. Okay, what about this small movement from that line? Like I've moved a little bit along that line, right? What about that point?
Okay. Uh, yeah. So, like, for any line that's not parallel to the null space, like you can actually draw another line that uh intersects this line that's parallel to the null space, right? So
Exactly. Perfect. And you can do this for?
all the points on the line. Yeah.
Exactly. Right? So I just took a
I
random
mean,
line which is not parallel to the null space. And you can actually represent each of these green points in this blue line as some parallel line of the null space. Right? it will be intersecting. If I shift it a little bit, I can shift it all the way here, and I will be able to represent all points, right? All points on the blue line, right? And every time I shift it, intersection is only 1 point.
Yeah.
And the third important point is ns of 1 is equal to 0. Ns of 2 will be equal to output.
Really? How is
Output
it 0? Yeah, output only.
ns. Okay, let's say ns 0 is 0, which is, this is better. Ns of 0 is a null space itself. Ns of 1 is shifted by 1. Ns of 2 is shifted by 2, and this will have a unique output too. O2 will never be equal to O1.
So that this actually ensures 1-1, and then like from what Chetan actually said before. Yeah, okay. Yeah, this was nice.
Yeah, since you're moving this parallel line along this entire blue line, and each blue line is just represented as one line on some shifted null space line, and we know each null space line has a unique output, this ensures that every point on this blue line actually has a unique output on the column space.
Okay.
Right, sir? This is just some random line. Why did we talk about a random line? Now let's talk about a line that we are interested in, right? The line that we're interested in happens to be the null space, I mean the row space, right? This perpendicular vector. Now, since we know there's a one-to-one mapping for any line, any line which is not parallel, the only condition was not parallel to null space, right? This was the only condition. Does
Yeah.
row space, what about row space that it will always satisfy this condition?
Row space and null space are perpendicular.
Exactly. Row space is always perpendicular to the null space, right? So no matter what matrix I'm given, the row space will always have a one-to-one mapping with the column space. Given any matrix, because we saw that given any line, right, any space which was not parallel to the null space had a one-to-one mapping with the column space. Row space will definitely have that follow the condition because it's not parallel to it, it's perpendicular to it. And so there's always a one-to-one connection between row space and column space. Now, if this mapping happens, then it is bijective, right?
Yeah.
And if it is bijective, it is only possible if rank of row space is equal to rank of column space. Easy, right? Because we saw it with the matrix function as well. Rn to Rn, only here it is possible to have bijective.
Yeah.
If it is Rn to Rm, where m is less than n or n is less than m, it is not possible to have bijective. It's only possible to have bijective when it's Rn to Rn. And that's what this is. This has to be, both of them have to be, this can be, if this is n and this is m, it is not possible. It is only possible if m is equal to n.
That's the reason why, yeah, dimensional row space and dimensional column space.
Exactly. I wanted to understand this entire concept using that, right? Understanding why rank of row space is equal to rank of column space is understood because of this.
Because there's a bisector mapping. Okay. So if you had a plane to a line, you wouldn't have a 1-1 and auto. You have it.
Exactly.
Maybe we can discuss Ankit's question too.
Yeah.
One thing also, like I was not able to listen to first 20-25 minutes of today's lecture. What
Didn't
topics
discuss
were
much.
you guys were discussing, because
Yeah, didn't
either I was able to look at the screen or just listen it.
Oh, we
So
were just
you were returning, I guess.
we were just talking about how when you have, say, a rectangular matrix, say 3 cross 2 matrix, right?
Okay.
And you give it an input that's lies in 2 dimensions. Because it's a 3 cross 2 matrix, you can only give it an input in 2 dimension, right?
Yeah.
But what that matrix will essentially do it will return you a vector that lies in the 3 dimensions, right?
3 close to, okay, let me think.
3 cross 2 times 2 cross 1. See what you get essentially,
Yeah, 3 cross 1.
right? 3 cross 1.
Yeah.
So it basically took a input from say 2 dimensions, gave you an output in 3 dimensions. Same you
Yeah.
do for say 2 cross 3. Give it an input of 3 dimensions. What you will get essentially is input in 2 dimensions,
In 2 dimension.
correct? Yeah. And we also talked about how each of the columns basically holds the information where your uh, unit
Or
vectors are going to map to,
yeah,
right? That's the information they hold.
yeah.
Another thing that we discussed was, correct me if I'm wrong, Shivne, that the dot product basically um, gives you the value by which your unit vector scales when you take the projection of a vector that does not lie on the same plane, right, Vinay?
Essentially, if you see a dot product, when you multiply matrices,
Hmm.
what essentially it is, it's dot product between ith row and jth column.
Correct,
So
correct.
essentially, the all the resultant entries of your resultant matrix will contain this value of ith
Hmm.
row
Hmm.
dot product with a jth column.
Hmm.
This thing is clear, but not the point that how
Yeah,
we see in your
we
way.
didn't actually stress upon it too much. We were going to discuss it. In fact, that point is still a bit hazy for me as well. What Atharva was trying to say is that if you have a point that does not lie on that particular space, you can take a projection of that point, okay, on that space, on that plane. Say you have a plane, or you can take a projection of that vector that does not lie on a plane on that plane, and the magnitude of that, okay, will represent by which your I cap and j cap have scaled, right? And that magnitude is nothing but the dot product of those vectors.
If you remember, Sir made us see this thing on Sunday's session, if you remember. The projection thing. It is the same thing, but we need to discuss a
Yeah,
bit.
yeah, we need to discuss it a bit more. I mean, I'm not getting the whole thing. I got bits and pieces from that, but
Is this what Atharva discussed?
yeah, yeah. This is
It is
actually,
the same thing now.
if you
He is
remember a
reducing
couple.
the dimension. Dimension reduction is done by
Yeah, no,
rectangular.
no, no, that part is there. Dimension reduction is there. The projection part is there. But that wasn't the point of discussion. The point of discussion was dot product. If you remember, a couple of days back, sir said, okay, I recently found out some new thing about dot products. That's
Yeah.
what happened. That day, they were actually, so these guys were sitting in sir's cabin and they were discussing dot products. Okay. And they realized, okay, something they realized, and that's what Sir wanted Atharva to discuss with us. So that was the thing. We'll be discussing it tomorrow. Don't worry. We'll be continuing it tomorrow. Atharva had to leave early because
Yeah, he had to leave.
yeah. What is this?
I
October.
think this was what Sir had put down after.
Yeah, yeah, right.
Yeah,
Correct.
Maybe when we took a few days leave, sir was planning to give some questions.
Yeah, he actually only took the leave because we had the quiz on 29th. So he was actually looking at the meeting length. Okay, and usually the meeting would go until morning 6 o'clock, 4 o'clock. But that week we didn't have any meetings past 12 or say 1, right? So he was a bit concerned that okay, it might um, uh, that we might not be discussing because of the pressure of the quiz. So he said, okay, let's take a break for 4 days.
For now, I'm focusing on these sessions more
Yeah.
instead of, because a term can be, I can revise always redo course if I don't score good.
Yeah.
But this is a certain different kind of opportunity to
Correct.
learn these things. I don't want to lose this thing as compared to that.
True, true. That's the same thing. See, I had two courses. Okay, I had two courses. I didn't do either because I was here discussing these concepts, and in the last week itself, I managed to save one course. But yeah, the second course, yeah, it didn't go as well, but it's okay. Even if I mess up in that course, I can make up in the next term. But these discussions, the intuition that you get from these discussions, right? You cannot get that in the courses. Yeah, but after getting this intuition, the courses make more sense. That's the beauty of these discussions, that once you discuss something here, those things make start making more sense. So
No, it's like a cup of tea for me to look directly for a column space of a matrix.
yeah, right, right.
At least for a small dimension that I can see like 3, 4, 5, 6, this much. It's a bit tough still for me to directly see a large data set with 10,000 rows and directly see
Mhm.
that what should I do. But I get a gist that
And we are
something.
actually trying to learn that as well, right? We are actually trying to learn the same.
Yeah,
We are,
we will scale up to it
yeah,
slowly.
right. We'll scale up to it.
Even for me, like I like the way he actually introduced a lot of topics. Actually, most of the things that he talked about were stuff that was in my course. Like he discussed clustering one day. I had clustering, and then he discussed PCA one day. That was also there for me. But I mean, I guess there were more details, but it was really nice to like hear Sir's perspective and how it
Okay,
applied in
okay.
the
Oh my
real
God,
world.
I'm still recording. I should stop.